that surprised me. I didn't even know that was going to be on there. So we're live right now. So welcome everybody to DragBoss Garage, Darin Morgan Induction. Appreciate you guys being here. It's been a long time since we were able to do a live chat. I'm telling you, I've been through the ringer, but I want to thank Darin and everybody else here that came from Facebook, because I've been doing a lot of work there, and the guys that are members here. They're just guys showing up. We already got 28 people here, so thank you. We had got hacked. I got hacked, I should say, and it was 23 days in purgatory is what it felt like. Working with YouTube was both a nightmare at times and a pleasure. But one thing that I can say is that we got the channel back 100%. We didn't lose anything. They didn't get any of our money. Now, YouTube is working with me actually we know who these people are because they switched the email that I had associated with this channel to their own email. So now we have their email. And actually what we did was we went in behind the scenes and I kind of hacked them. And that's how I got the channel back, by switching, doing what they did to me. YouTube got me in there, or Google got me in behind the scenes. I switched the password and did some other stuff and commandeered and took the channel back. So that's how it works. So they're actually looking for them. They sent me a text today saying that they have some leads that they're going to, you think it'd be easy. It's an email, you go right to the source, but it doesn't work that way in the world of electronics. So I will give you this piece of advice, guys. If you got antivirusware, get it working. Get malware bites, do something, because I'll tell you, you don't want to go through this again. Now, I will say this. Someone had texted me or messaged me, Trey. Trey told me that his credit card got hacked. Now, I don't know if there's a correlation between that, because no one else has reported that, for one. Two, Darin and I don't have any access to your credit cards. It all goes through YouTube. I don't know your numbers. I don't see them. So I wanted to put that out there, though, as a public service announcement, so you guys can pay attention to that. I will tell you this. I've now kept my passwords in a paper log, because trying to remember them or let password manager, I'm not doing any of that. So you might want to think about that and change your passwords often. I'm telling you, I changed one for YouTube today, and I just changed it like a week ago. So, piece of advice. Now, I will tell you this. Darin and I are going to PRI in December. That's the 11th, 12th, and 13th. So if you guys are going to go there, look us up. We got a lot of interviews to do. We've already got a bunch of guys set up, and I'm pretty excited about going to PRI. I'm going.
Yeah, we're gonna interview Macklemore. He's doing a lot of machine work and stuff.
Yep.
Yeah, we got like 3 lined up, 3 heavy hitters.
3 heavy hitters, and I got about 5 already. So I'm going with APD, Advanced Product Design. Thank you, John Kyle, for the invitation and take care of everything. I appreciate that. So there's someone here, I don't know, and not Nutbus, okay, from Norway. Thanks for being here from Norway. It's probably dark there right now and snowing. But we're going to do this live chat. Now, this is an open one for everybody. I put an invitation on Facebook because I've been working with Facebook and have 20,000 followers as of yesterday, which to me, that's a lot of followers. So I appreciate you guys being there, and I appreciate the YouTube crowd too. So I'm kind of bringing them all together. That's kind of my plan right now. And we're going to kind of go social media. So stay tuned.
We're gonna interview the people we want to interview.
Exactly.
The people that are bringing new stuff to market, stuff that I'm interested in.
Yes.
I really only talk about shit that I'm interested in anyway. So, you know, these people don't pay. They're not paid promotions. These are guys that are forefront, that are bringing stuff to the market, that aren't relying on the aftermarket. They're doing it themselves.
Right.
And that's commendable.
It does. It says a lot about a person, and the individuality, the fact that they have a lot of ambition and drive. So
the way this is going, the way racing's going right now, it's kind of like the 80s. If you didn't have it, whether it was money or product, you either had to make it yourself and work harder to get it. We're going right back into that. It's
got to be.
If we don't have it, we're just going to have to make it, because the aftermarket is not going to help us anymore.
Well, it's basically owned by one company. You know, Race Winning Brand seems to own it all, so we won't go there at this time. But I want to give some congratulations. Thank you. We appreciate you for the donation, $20 Canadian. So glad to see you guys here again. I look forward to these meetings more than I could go speed shops and buy tools in the 70s, 80s. Yes. Thank you for being here. We appreciate that. You know, any money that we go here goes right back into DragBoss Garage and Darin Morgan Induction. Help us bring this to you, this knowledge. But tonight's live chat's about dynos. You know, we all talk about dynos, dyno that, dyno this. It made this much horsepower, this much torque. You know, my own experience, I've had 3 dyno sessions, all with the same guy, a guy named Todd Quinn. I think Darin even worked with him at one time.
Yes, I did.
Platinum Engine Service in Newark, Ohio. Great guy. It's like when you see my dyno videos, I mean, the place is a palace. I love the way it's set up with big screens. I mean, it's state of the art. So I stick with the same guy because then you're getting the same equipment every time and your results are the same. And that's key.
And sorry to interrupt, but Todd doesn't do anything half-assed.
No.
Todd is a perfectionist. He's a professional. He's dedicated his life to this. So, yeah. Like
you. I mean, and that's what you need. If you want to have the same results, you got to have good equipment to start with. So I will tell you this, the dyno, the engine back there, that's one that made 769 with a 4150, 775 with a 1050. So that'll probably go back there and we're going to dyno that again. But that dyno session, the last one I did, that's 21 hours. I timed it. That's 21 hours plus the cost of it's $1,000 right there to dyno an engine. By the time you drive there, it's 3 hours away, gas, the cost of everything, the fuel. So it's not a cheap endeavor. So if we can help you get the best out of your dyno experience, and that's what Darin's going to do, that's what we're trying to help you with.
But see, you did it right. You go back to the same dyno, the same guy, an established baseline.
Right.
So you know if you make a gain or a loss based on your previous data,
sure,
the same test conditions, that's relevant data. Again, it's all relative.
Are you ready, Darin?
Yeah, I'm ready.
All right, here we go.
All right. Over the course of 40 years, when it comes to dyno data, everybody says everybody's dyno's different, everybody's dynos read different, and comparing dyno sheets, whipping out a dyno sheet at the racetrack is worthless. At the racetrack, you prove what the dyno said in your mile an hour ET and relative to the pack. So how much do dynos vary? Oh my God, 80 to 100 horsepower. That's pretty much been the same since 95. Now, why do they vary? We're going to get into that. But back in 95, 6, 7, 8, all the pro stock teams played musical dynos because we were really sick of comparing dyno data or looking at other people's dyno data and going, okay, well, why am I 2/10 faster, or I'm making 20 more horsepower and I'm 2/10 slower? I mean, we had to quantify the acceleration rate of the engines as well, which is different than what a lot of dyno data gives you, and we'll get into that too. So, Larry Morgan, Orndorff, Morrison, Powick, Maskin, Schmidt, all of us played musical dynos. We shipped our engines all over, trying to get this established baseline. Okay, well, his dyno's 20 high, his dyno's 30 low. Now, how much variance do you think was amongst the pro ranks? These guys do this for a living, some of them. There was 100 horsepower difference. So why is there 100 horsepower difference? We'll get into that too. But the main point I'm trying to make here is the dyno data that you get from where you go. Don't play musical dynos. Don't take your engine to 5 different dynos because you're going to get 5 different answers. Stick with your engine builder. Stick with his dyno. That's an established base. You know, as engine builders at BES or anywhere else, job shops like I work for, what we do nowadays, there's no research and development. This is throw what you know. We throw what we know at it. And the more we know, the better we can serve our customers. We're selling a power price point. The customer wants this much power, needs this much power. And we say, okay, we can do that. And we do that. That doesn't mean that's all the power that engine can make. As a matter of fact, every time an engine is done off the dyno, that dyno data is scrutinized by Tony Bischoff and Preston and myself, and we compare notes. Because the next year, when that customer comes back, we already have a game plan. There's no way to build an engine for a set cost. We're selling a set price, set cost. Could we make more power? Absolutely. But the cost has to go up accordingly. And a lot of times when people price power, if you get that, but there's a lot left. Okay, so every year we've already have a game plan. When that engine comes back, we say, if we increase the cross-sectional area, we increase the taper, we change the cam this way, or we do this, or we do that, and we narrow the bearings, or we can gain another 20, or we'll get another 30. So the next time that customer comes back, he's offered that. Listen, for another 10,000, we can invest more time. It's time and money. We can invest more time, and we've calculated this out. We can get you another 20. We know we can get him 30. We tell him 20 for that $10,000. And the next year, it's another 10,000 for another 20. And the next year, it's another 10,000 for another 20. So why does it work that way? Because we don't have engine development programs anymore. Job shops work off of that cost of power. So we know we can make more. So if you sell 2,000 horsepower for 45 grand, and there's another 500 in it, you can't, the engine builder would have to close the doors if he invested everything that he could to get that next 500. So we know the next time the customer comes in, we say, okay, we can get this for this. And a pro stock deal and a competition eliminator deal, you're going for the throat. You're going for everything you can get. And that costs time. And time is money. So the guy spends 50, 60, 125 grand on an engine. You say, listen, if I build this engine, it'll be a record setter. It will make enough power to run on the record. That's what you're selling the customer. Is there more left? Oh yeah, there's always more left. Always more left. It's time, money, perseverance, and work. That's all it is. So unlike a team that works on that same engine all the time, bumping it up and bumping it up, a job shop, an engine builder sells an amount of horsepower at a given cost. Now, where does that leave us when it comes to setting a record? If a guy comes to us and says, competition eliminator, whatever class it is, it doesn't matter. You're competing as a job shop against other people who have done the research, done the development, and reached that level. So now the cost goes up in order for us to do that amount of work to get to that level. Now the dynos that we use, they're all different. Let me say that first and foremost, straight up front. No two dynos agree. I've seen shops that had 3 or 4 dynos in a row. They're 20 horsepower different. One will make 25 foot-pounds more, one will make 25 horsepower more, but that's a quantifiable number. You know that. Those guys that work there know that. Those engine builders understand that. So when they're selling a price point and a power at a certain price point, they understand that their dyno at this level will be a record setter, and you're right here, and they have to bring you up here. Where somebody else that's making 100 horsepower more on their dyno knows that they have to make that much power. So it's all relative. So why do dynos disagree? Hold on a second, I got it. I will replace that camera one day. Why do dynos disagree? Well, first let's get into correction factors. And basically drag racers use two. And some drag racers, some engine development places use a completely different correction factor than even this. And you don't know that. So you're going to a dyno that uses this correction factor. And by the way, I've highlighted the two major correction factors that most engine builders use. These are pretty much OEM stuff or specific to dyno, DPAC, whatever. So there's 25 horsepower. If you're making 1,500 horsepower, there's 50 horsepower difference between those two dynos just in the correction factor alone. So you don't know that. So you're looking at a dyno that's 50 down or 50 up compared to what you're used to. So you need to quantify what their correction factor is as well. So the standard J607, that's pretty much what everybody used forever, which is 29.92, 60 degrees Fahrenheit, and 100% mechanical efficiency, okay, and 0% humidity. It doesn't correct for humidity. So for decades, if it rained outside, you would not dyno. It's worthless data. Because once those water grains reach a point where they're displacing oxygen molecules, don't dyno. It's worthless. Because what happens, the water's putting the flame out, and you don't have the same amount of oxygen, so what do? You throw a lot of time in at the engine, advance the cam, and try to bring the power up. Well, that's worthless, because you're dynoing under conditions that you may have at the racetrack at some time, but it's not relevant to actually tuning the engine on the dyno. Glidden, a lot of pro stock engine builders, Orndorff, Lerman, we wouldn't dyno on a rainy day because that's worthless data. Anything over 60% humidity, actually 50% most people wouldn't, but 60% humidity, you're starting to displace your oxygen and putting the flame out, slowing the flame down. So the data that you get is not relative to the corrected data that you had before. Then you have the J1394. Now these change, by the way. The 1990, 1992, 1994, and 2004 numbers are a little different. Now what this does is it actually takes into account mechanical efficiency. So it's looking at friction power a little bit, and it also looks at the, I think it's 23 degrees or 33 degrees relative humidity. So it's taking humidity into account up to the point where it doesn't displace the oxygen and actually start narrowing the numbers. So why do you do that? Why do you use different correction factors? Well, you're trying to have the least amount of correction in your data. So if you have a correction of 1.009 or 9-10% on a 500 horsepower engine versus a 1500 horsepower engine, there's quite a difference there. You want to correct back the least amount you possibly can. So you want to use a correction factor within wherever you're dynoing, whatever that barometer is, and your average relative humidity throughout the year. You want to pick a correction factor that actually kind of covers those conditions. So that way you're only correcting back 1 or 2%. That's fine. But when you leave the math up to correcting more than that, it skews the numbers. So here's the standard 29.92, 0% humidity, 100% mechanical efficiency. We'll get into that. And 60 degrees Fahrenheit. Well, that's the lowest temperature. If you look at the Reid vapor pressure, you look at the moles of water and everything else in the air relative to that correction factor, it doesn't take anything into account. There's a lot of correction there. You could have 4, 5, 10%, 12% correction on that. And again, the idea is to have the least amount of correction possible. Because when you're mathematically correcting 9, 10, 12%, there's a lot of room for error. I mean, you could be off 10, 20 easy. That's not good data. That's not going to help you. The SAE 77 degrees Fahrenheit. Now, this was, I think, this was the OEM switch to this. Some of the teams started switching to this because 77 degrees Fahrenheit is close to the temperature that you actually run in on the racetrack. So between 68 and 85 degrees, this kind of splits the middle. 29.92 standard, but it takes in humidity. It takes that into account. So it lowers kind of the mathematical correction, because where are you going to live in the United States that's anywhere between 15 and 50? Well, there's a lot of places. Where are you going to live where there's zero humidity? No, nowhere. You're going to mathematically correct a lot out of that. Plus, it has 85% mechanical efficiency, so it's taking into account some of the friction power and everything else that's so. And this is the correction factor that like OEMs use now. So they've lowered the barometer and went back to 0% humidity. I don't know. I just threw that in there because that's what they do. Absorber type. Oh my God. If you play musical dynos and you take your your engine to multiple dynos, whether it's a DTS or a Superflow or a Stuska or a Stall or some custom absorber, we don't know what absorber it is. Absorbers load the engine differently. They let the engine release differently. Their control mechanisms are different. You have so many different ones. You have hydrokinetic, which is the Superflow, which is the DTS, the Stall. That's a water, like a torque converter on water with water. And I'll get into temperature later. Hydraulic shear, which is like a torque converter. Eddy current, which is opposing flux. And you can control an eddy current dyno a lot better than you can a water dyno. An eddy current can accelerate or decelerate or control even gear change. You can even make gear changes with the dang thing. Very reactive and very accurate. And then friction brake. That's what they had back in the 50s, 60s, 70s. It was an actual brake. What you did is you accelerated the engine up and then you drug it back down with a brake, or you took it to a certain RPM. And when I was younger, I got to see this. Unlike a Stuska dyno, you'd have an RPM guy, you'd have a torque guy, and you'd have a horsepower guy, and you'd have a dyno operator, because it was all gauges. So you would load the motor and you would bring it down to an RPM, let's say 7,000. And you'd load it at 7,000 and hold it. And all these guys would write those numbers that the dial was reading down on a piece of paper. That's how we used to dyno. It wasn't a dynamic acceleration like we do now. And God, we're going to get into that. So, and inertia dynos. Inertia dyno, completely different acquisition. For an inertia dyno, it's basically the time it takes the engine to go, 100 RPM, you can put it in 1 RPM increments. It's basically an acceleration dyno. It tells you, with this given weight, this engine is going to accelerate that weight at this rate. So there's no power number. There is, you can calculate it, but it's basically time. So if you put a more powerful engine, if you have two engines of the same class, same displacement, everything, you put one on there that accelerates the inertia dyno quicker, it's going to go faster down the racetrack. Simple as that. But inertia dynos can be pretty hard on engines because a lot of times there's a lot of, you can build a lot of heat in the engine and the variables can get away from you. We'll talk about that too. Instrument and testing variables. Strain gauge temp. Oh boy. And everybody had superflow dynos. That was the most affordable, level, accurate relative to the money dyno you could buy in the 80s, 90s, even into the 2000s when DTS and other things came out. A lot of people had their Stuska dynos. And the Stuska absorber is different than a superflow. The strain gauge type. I'm getting off topic here. The strain gauge itself, there are a lot of different strain gauges, and I'll get into here later how those react. You have aluminum, you have steel, you have expansion, you have contraction. A lot of different, and they all react different. And they all thermal drift, and they all change relative to the temperature in the room. So you have to monitor that. Oil temp. You need to monitor the oil temp in and out. You need to measure the water temp in and out. The cylinder head temperature front to back, as well as the average coming out. You also need the intake manifold temp. If your intake manifold's 25 degrees cooler and you walk into the handle, yeah, it's going to make more power. We're trying to narrow down the changes. We need to see 1 horsepower change on a 1400 horsepower engine. That's 14 horsepower. We need to see 1/10 of 1 horsepower. We need to see 1 horsepower. That's 1/10 of 1 horsepower. Less than that. Intake manifold temp. Fuel temp. Fuel temp changes the atomization, the phase change, droplet size, oil pressure, in and out. 5 degrees of oil temperature can be a horsepower or 2. Oil pressure can be, 10 pounds of oil pressure can be 5 horsepower. You have to baseline all this stuff and document it in order to know actually, to establish a given baseline that you can work from. Absorber inlet water temperature, big one. Whether it's a superflow or a D-pack or anything else, at Morrison, we pulled water right out of the main, which is like 62 degrees Fahrenheit, cold. And a lot of people will have water tanks. Well, if you're dynoing throughout the day, that absorber temp water inlet is rising. And pretty soon it will reach a point, especially on superflows, where it will start cavitating the turbine. And it will chew that dyno absorber up. I can't count, probably at least 20 dyno absorbers that I've rebrazed up and remachined and then recoated because cavitation completely wiped them out. And pretty soon on a superflow, it's kind of easy to see. You have to keep screwing more boost valve to it to get it to bring the engine down to the same point, and you pretty much know that your stator and turbine are cavitated to death. It just eats it up. So you get in there with brazing rod and remachine the whole thing, and then you actually, my brother at Ray Morrison, he actually messed with the spacing and everything else to use less boost valve and walk into the curve easier. All these things these engine builders do to achieve a given baseline, nobody really knows about. The acceleration rate. If you go to a dyno that has a Stuska that's running through the water, I'll explain that here in a second, or to a superflow that's accelerating at a given acceleration rate, 500-600 RPMs per second, those could be completely different curves, and the fuel curves will change dramatically, especially with carburetors. It'll change dramatically. With EFI, it'll change, but with carburetors, it's like if you accelerate an engine on a dyno at 300 RPMs per second and then mimic first, second gear at 1,000, 1,200 RPMs per second, that fuel curve will alter completely. And with carb guys, that's always a battle. The acceleration rate, if you play musical dynos, you go from dyno to dyno, you need to ask, what are you accelerating this at? Or are you just trying to run through the water and document time? Because the old Stutzkas with the D-packs, what you could do, and you could still do this with a Superflow, is you set, instead of telling that dyno, I want 600 RPMs per second, you go, I want the absorber to release at a given rate throughout this curve. I don't want it to control the RPM. I just want it to open that valve at a given rate. And that takes a little playing with the engine. But what that tells you, and this is what Glidden looked at more than anything, is fuel flow and running through the water. If you have a given rate that is the same release every single time, and one engine pulls more fuel and runs through that water faster, that's the one that's going to accelerate on the racetrack quicker. But with a Superflow, it's controlling, it's holding that engine at 600 RPMs per second. So you could miss a lot of things as far as skewing the fuel curve and the acceleration rate and that engine's ability. On the Superflows, we usually looked at fuel flow. If the engine made the same power and moved more fuel through it, and it wouldn't, what we call choke on the flow, choke on the fuel. You could just put fuel to it and it wouldn't choke on it. And in other words, there's enough air going through the engine to where if you could put more fuel to it and then load that engine down hard, it's going to use the fuel. If you have an engine that wants to burn lean and you load that sucker hard, there's no fuel to accelerate. Inlet air temperature. Edgar Smith was going to come on tonight, and he was going to talk about some of the creative interpretation of the rules at the Engine Masters Challenge. So all these variables have to be controlled, and when you walk into the handle, they all have to be the same as the previous pull. Otherwise, like I said, 5 pounds of oil pressure, your oil heats up, you could be 5 horsepower different pretty dang easy. The evacuation, the inlet flow in the dyno room, is it ducted? Is it a blow through? Is it a blow over? How does that air enter the room? How does it go over the carburetors? How does it evac out of around the exhaust? That plays a huge role. People wonder why dynos vary. There's a huge variance right here. The room itself has to be built to very defined specifications in order for you to get reliable, consistent results. Accuracy is one thing, consistency is another. If you have a dyno that's consistent, that you can take an engine off, rebuild it, put it back on there, it makes the same power, and you could do that over and over and over again, that's worth its weight in gold. And when you have a dyno that fluctuates, there's no higher level of aggravation than that. Temp humidity control. Are you pulling shop air, outside air, or are you atmospherically controlled? We, at Rares, we got tired of fighting the correction factor, changing throughout the day. I mean, that's a lot of variables to keep up with. When you're trying to see 1/10 of 1 horsepower change and the barometer's dropping and the water molecules are going up and each pull you have to, that's a pain. So what they did was he bought a $60,000 system to put on the roof that delivers, I think it was 2,800 CFM consistent. They're built for hospital dyno or hospital operating rooms. So they have a consistent airflow out of the room to take all the bacteria and everything else out. There's no stagnant air. But what it does is it takes whatever ambient temperature you have and cools it down to about 45 degrees, which wrings all the moisture out of it over the coils. So it's dry air. It's 45 degrees dry. Then it's heated back up to 70 degrees, and in a tunnel, there's a mister that takes 20 minutes to stabilize to 50% humidity. So no matter what day it was, just so long as we could walk in that dining room and it was 70 degrees, 50% humidity every day, all day, never changed. That's what it took to develop those engines over time and to know. And a lot of strain gauges are different too, and they react differently too. So the operating temperature back in 90 to, when did Superflow come out with it? It was I think it was about 2004. They came out with the steel expansion gauges instead of the compression dog boat aluminum gauge. And what it was just a dog bone gauge. And this is what you're dealing with here. This is a honeycomb that's placed on a metal, whether it's steel or aluminum. And as the aluminum compresses or pulls apart, the distance between those blades changes. That's a relative voltage change. It changes the resistance in that stack. And then you have what's called I'm an electronics hobbyist, so this is cool to me. They have what's called a Wheatstone bridge. And basically it's 4 resistors, and you take the difference going through this, and they're very, very accurate. Very, very accurate. As a matter of fact, before this, they put one in front and one in back. So you actually have the input and output variance and voltage as that strain gauge stretches and contracts. And it doesn't, you're talking, what, I don't even know, 7/10 millionths of an inch stretch. And this thing's able to tell you the amount of force over that much range. It's pretty amazing. But back in the old days, when we had the aluminum dog bone expansion, okay, in other words, there was an aluminum piece about that long, and it had 2 eyelets at each end, and it connected to the Superflow dyno. And it did have a stop on the absorber, so if it snapped, it could only go about 1/4 inch before the absorber stopped. But the elongation of aluminum, it had a lot more elasticity than steel does. So back then, that was probably the best choice. But aluminum also has a thermal coefficient that varies wildly. So as it got hot and expanded, the power would change 10, 15 horsepower. So teams were actually putting hair dryers and thermocouples on the dog bone to heat it up to a given temperature before they laid into the handle in order to maintain consistency. Because you'd start the day off, let's say it was a 70 degrees day, well, that dog bone would get 200 degrees or 150 degrees at least. By the end of the day, dyno and the engine, well, that's 10, 15 horsepower difference. And the strain gauge is throwing you off. So in order to maintain consistency, they would preheat that thing and keep that temperature and monitor that temperature while they were pulling the engine. Calibration curve, that's another thing. Are you using certified weights when you calibrate that torque arm on the dyno, or are you just going to your local sports and getting some weights that say they're 35 pounds and throwing them on there? Or are you measuring those actual weights on a certified scale and then stacking those? And this thing isn't perfectly linear. No strain gauge, no transducer is perfectly linear. Even a linear strain gauge has a slight curve. So you have to tune it, calibrate it within its range, the flattest range possible. So the calibration curve can also throw it off. And with modern superflow dynos, are they in digital mode or are they in analog mode? Are they heavily filtered or under filtered? Because we have filters now. Especially if you're in a digital mode, you could put a 3 or a 7 filter in there and heavily, what they call loop filter that data, and you'd be actually making on someone's dyno 800 foot-pounds, and you're only seeing 770 on this because it's this loop averaging filtering input into the dyno. So you could go to 10 different superflow dynos that all have different filtering and get 10 different answers. So what am I getting at here? It's all relative. That engine builder knows that dyno like the back of his hand. Those numbers are his numbers, just like my flow bench numbers are my flow bench numbers. If a customer takes that engine to another engine builder, dyno, or what have you, the numbers will be different. How different? Well, going back to the calibration, the correction factor. There was a professional engine builder whose engines were 85, sometimes 100 horsepower higher than anyone else's. If you took his engine and put it on Rare's dyno or BES's dyno, it'd be 80 to 100 down. Now, they were still competitive. They still kicked ass and took names. That was just their power level. But again, you don't compare dyno sheets at the racetrack. He had a Stuska dyno with a DPAC acquisition system. We can go into that too, because a DPAC has an inertia factor. You have to tune each engine's inertia factor. In other words, its internal weight, the rotating mass, the reciprocating mass, that all has to be canceled out. Otherwise, that goes into the mechanical efficiency. If you have one engine with a bob weight of 2600 and another one at 2200, well, the one at 2200 is going to accelerate faster and make more power. But if you don't cancel out that inertia factor, especially with a DPAC, the numbers are going to vary wildly. So he had a DPAC with a Stuska with his custom inertia factor that read 100 high and bought a superflow. Actually, I think it 2 superflows. And his numbers were so low, he says, I can't sell that. I can't now tell my customers that all these engines are 100 horsepower less, which in my book he should have. But he had Superflow write a custom correction factor to bring all of his engines back up to what that Stuska told him they were. It's his correction factor. It's his baseline. That's why I say, whose ever dyno you use, go back to that dyno. That's the established baseline, and start making gains, or God forbid losses, from there. All right, I'm ready for questions. Yo, you still there?
Right on. You can't hear me if I'm off the screen. I was talking.
I can hear you.
Darin is here breaking the brains. Yeah, no doubt about that.
I'm just touching the surface here.
Yeah.
I'm just
Crazy,
trying to
man.
explain why everyone's different.
Well, the fact I didn't know, like an operating room where I worked for many years, is that they have that system in a dyno room. You know, an operating room, the air changes, I think it's like 75, some crazy number like 75 times a minute or something. You know, that it's some crazy number like that. You
You
know, when
got to
they do
carry all that, yeah, all the bacteria and
potential,
bad
yeah,
stuff out of the room. Positive flow system.
yep. And now they're wearing enclosed suits. If they do a total joint, hip or knee, they wear like a spacesuit, you know, to help prevent bacteria spread. So it's pretty crazy, I'm telling you.
MRSA has always been a problem.
It's always there, though. Everybody has it on their skin. It's just a matter of whether it's going to infect you or not. You know, that's the issue.
That's what killed Joe Mondello.
Was it really?
Yep.
I didn't know that.
Yep.
Now
He got it twice.
Did he really? Well, you
He
become
usually don't survive it once, but he got it twice.
You know, something that Scott Foxwell's here. It's good to see you, Scott. But he had a comment here. He said you didn't touch on dyno room exhaust systems.
Excellent question. First off, if that exhaust header is going to, I'm trying to anthropomorphize here, see atmospheric pressure, it has to be at least twice the diameter of the collector. Otherwise, you're instituting secondary tuning factors into that tube. So if you have a 4-inch collector, you better have an 8-inch tube hooked up to it. Otherwise, it's not going to mimic what it sees in atmosphere. Number two, the airflow, I kind of touched on that, whether it's a hooded, whether the hood comes down over the carburetors or throttle bodies, whether it's a blow over, whether it's a directed airflow over them, that's fine. Either method is fine. But what are you doing to the airflow on the sides? There should be airflow on the sides of the engine to evac any pollution that's taking or getting into the room that those carburetors or throttle bodies can take. And you have to have a good room, a good tuned, designed room that does all that for you. I've seen dyno rooms. I saw one dyno room. I walked in and I just walked back out because it was like there was enough exhaust pollution in the room to kill 20 horsepower.
Wow.
So, and if you bolt a tube that's not twice the diameter, the engine will usually nose over like a rocket ship because what you're doing is you're just increasing the collector length, or you're splitting the wave or the harmonic, and now you've got two coming in. So now that screws up the fuel curve. Sometimes you'll see a fuel dip. Sometimes you'll see it has to be either open out in the atmosphere or at least twice the size. That's what. And Mr. Foxwell, if you could add to that with another question, I'd sure appreciate it.
I'll look down and see if Scott does. Now, this kind of brings into play just what you were saying. And you could do a whole presentation on this. So just hit the high points on this question, Darin. Jacob says, if you were going to design a dyno, how would you go about it?
You're asking the wrong man. I'm not an electrical engineer. I don't have the expertise to answer that question.
How about this one? If you're going to design a dyno room.
A dyno room?
How would you go about it? We'll change it.
Well, I would have a hooded constant flow system over the carburetors or throttle bodies or inlet, wherever it is. I would have a constant flow system. Even if it was a supercharger with a snozzle sticking out there, I would have that hood right over there. Okay. There are some downfalls, pitfalls with that. Whatever you do, do not seal a hood to the carburetors. In other words, if you bring your hood down and it's sealed on a flat plate to those carburetors, that destroyed a Pro Stock team for almost 2 years.
Wow.
Because the inlet flow was governed, the inlet flow velocity and volume was governed by the fan, and they brought that hood down over the carburetors. So initially when you walked into the throttle, it was supercharged, and it would run out of volume and work on the upstairs volume, and the power, the fuel curve was altered. Everything was altered. It couldn't qualify. Couldn't qualify. That company was Rare Morrison. Wow. My brother figured it out. He he cut louvers in the side and put flaps, just cardboard flaps. So as the engine started to run, all the air was shooting out the sides, and those flaps were at 90 degrees. And then all of a sudden, at about torque peak, they went and shut. Let's run that air. That's what spurred the constant flow system, like in operating rooms. That's how he got onto that. And how he got onto that is I was working for Larry Morgan at the time, and we had sent an engine there to Dyno. And he was like, it's no better than ours. It's got the same problems. It's got the same fuel flow. It's got all the same issues. So I think it was like for 6 months, we were just scratching our head. And then they sent an engine to Larry Morgan. So we dynoed and was like, it's way off. The fuel curve is 20 pounds an hour different. It's skewed. It's got a lot of fuel down low, and the nose is over. It's like, what's going on here? And my brother put 2 and 2 together and went, oh, it's that.
It's like
so if you have a hooded system and you bring it down over the carburetors, just leave a space, or use the louvers to actually see how much air the engine's taking as it's taking it. But you have to have a pressure equalization there.
Mm-hmm.
You can't supercharge the thing with the fan.
There's a guy on YouTube. His name is Nick's Garage. He's from Canada. Now that guy does he's a Mopar man, Ty, so you probably watch his channel, but he does a lot of dynoing. And I know he has the hood, but now that I see what you're talking about, I'm going to go back when I look at one of his videos, probably later after this, and see where that hood is and see if it's over the carbs or whatever. Because at one time I can see that, and other times he's got a camera right over the thing looking at the fuel going through the carb. So there can't be a hood on it unless it's inside there, but I don't think.
Well, sometimes you can bring a hood down and seal it to the plate just as long as it's vented.
Okay.
To where the excess pressure goes out. But I like the flaps because you can see how much air the engine's taking relative to the flap angle.
Eric's got a question. He says, Darin, I have an SF901 dyno. It's old. Should I try to stay with SF for data acquisition or retrofit with your dyno data acquisition software and strain gauge?
You should stick with what you have, what you know, and what you've worked with. Don't institute any unknowns into the system, because that's going to lead you astray. That doing what you're proposing here could waste a year. You know that dyno. You know it like the back of your hand. You know all of its little idiosyncrasies, its issues, its problems. It's a 901. It's probably got the cards in the back don't connect a lot of times. It's got drift on the dog bone, if you still have a dog bone. What we did is we went from an expansion dog bone to a compression Z-steel, which is more accurate, and we put arms off the dyno, and that prevents, when you put the dog bone like Superflow has, and this you can do, it's really close to center. So any jerk in the engine is transferred really hard into that dog bone. If you move it out here, it has a lot of, it takes a lot of that out. I like the 901. Well, I like the 901 because that's pretty much what I was raised on. I've seen more pulls. I mean, we used to do, one year we counted 5,600 pulls. So 3,500 pulls a year would be a normal year. So how many dyno pulls have I seen in 30-some years? God, that's got to be 60,000, doesn't it? Anyway.
Yeah.
I like the Superflow because I know it like the back of my hand. I've rewired them, I've calibrated them backwards and forwards, and I know them. And then we went to a Superflow with a D-Pack, and now that D-Pack Dave has passed, that's no longer an alternative. And I like the D-Pack system. I loved the D-Pack data acquisition system because it would let you tune the inertia factor. It would let you see the time it took. It would let you control the rate of acceleration or be able to do what we call a servo pull. I want to start the servo here and release it at a given rate and then watch that engine accelerate through the water. And the engine that accelerated through the water faster would be faster on the racetrack, hands down, no problem. That's the way it is. Even if they made the same power at 600 RPMs per second controlled acceleration rate. The other thing is, when you're dealing with acceleration rate, you go to one guy that's 300 RPMs per second. You got to remember, some of these things are 1,200, 1,500 RPMs per second or more in first gear, second gear. When you slow the acceleration rate down, your fuel curve gets nicer, everything gets smoother. Well, that's not real world. High gear is like 600. I want to see what it's doing dynamically on the I want to try to mimic that and see it. So if you go from 300 to 600, you'll see that your fuel curve is a lot different. Then you go to 600 to 1,000 and it's like, holy crap. And then you plot the difference in the power drop between engines between 3.6 and 1,000, and that's going to fill you in a lot of information as well, even though they make the same power at 600 RPMs per second. It is a fact. Two engines can make the same power on the dyno and accelerate differently on the racetrack.
Wow. Well, you got to think about it. I mean, it's not going to have the two different cars. They got two different transmissions, two different rear ends. Everything's different about that, even though they may be the same.
And you will see that on an inertia dyno or a servo rate.
Mm-hmm. Now, this is kind of just right down the alley of what we're talking about. Terry Grover says, I see more inflated horsepower dyno numbers on YouTube than I've ever seen in my life. Maybe Darin can address this too. You know, you can make it whatever you want, right? If I want 800 horsepower, I can make that engine make 800 horsepower on the dyno, right?
Yeah, well, there was a thing, a terminology, a slang terminology that we used to use called knobbing it. When you're knobbing the engine.
Yeah.
There's a knob underneath the Superflow 901 dyno.
Okay.
It is a torque cancellation knob, and it can swing like 20 foot-pounds either way, positive or negative. So when you have the engine on the dyno,
yeah,
that engine will react with the strain gauge. And you just put it on the torque knob and you see, oh, wait a minute, I'm 2 foot-pounds positive with the engine not even running. That's just loading the strain gauge, bolting it to the dyno.
Right.
So you reach underneath there and you cancel that out. And then you put the torque knob back to horsepower or whatever you want to read. Back then, it was really easy for engine builders to knob it. So if you sold 1,000 horsepower and it made 990, you could reach under there and screw 3 foot-pounds in it, make a yank it. The dyno sheet says it made that, and
there it is.
Out it goes.
Here you go, Terry.
That was a common practice because, one, a lot of customers didn't understand that the difference between 990 and 1,000 and the way the engine accelerates, it's not that freaking important. I mean, but you're also selling power for money. So
that's it.
And then there are the total cons, liars, thieves, and that just knob the shit out of it and put 10 foot-pounds in it. You know, those guys exist.
Sure they do.
Or existed. I knew a lot of them that did exist. They don't exist anymore.
Now, I don't know. We'll put this question up there, and it might be related to what Adgar Smith was going to talk about. So you might know this. I'll just throw it up there. But Greg says, I'm pretty sure I know who had the dyno that was 80 to 100 horsepower high.
There was two engine builders.
Okay. The names
both aren't around anymore, so I'm not going to.
There it is. They're going to remain innocent at this point in time. So, John, thank you. John Salvatierra from Syracuse, New York.
Oh, a Freud, a Heenan Freud. Oh, that's the Cadillac. That's the Dyno of Dynos right there.
He's faster than me. He's already got that reading. I was going to say, hello, Tim and Darin. Great talk and very true. I ran a Freud eddy current dyno, always checking and calibrating. I got to know the guys in the meteorology calibration lab real well over time.
Yep. People have no concept what it takes when you're at a competitive level to baseline that dyno and keep it that way throughout the day to where you can tell changes. It takes a lot of effort. And it's like the variables I was talking about is instrumentation and testing. Okay, oil temp, water temp, cylinder head temp, all these variables, and my brother did this at Rare Morrison. Okay, you got the air system. You got that baseline. 70 degrees, 50% all day, every day. Don't have to worry about that. The only thing that moves is that barometer. And it's not going to move more than 2 or 3 points or 10 during a normal day. So now you have these to contend with. So if 5 degrees of oil temp or 5 pounds of oil temp could be 2, 3, 5 horsepower, you have to be able to make sure when you walk in the handle, when you make that pull, that it's exactly the same as it was the last pull.
Yeah.
So what he did was he set all these variables up on a graph. And you can custom design graphs and whatever you want on all this software. And it had a green line. It was about 3/4 of an inch. And what he would do is he would mess with the engine. Let's say it got too hot. Well, he'd either shut it off and wait for the temps to come down until they started falling, and they'd fall below the line. He'd fire it up, and he knew about how fast it would warm up certain things, water, oil, and everything else. And unless all those variables are in that green line, you don't walk in the handle, because to do the data is worthless. It doesn't help you a bit.
Okay. Scott, thanks for that $20 donation, John. We appreciate that. Thank you. Scott comes back and says, I don't have anything to add. I've seen all sorts of different exhaust systems on dynos and always had my concerns. Darin, thanks for confirming some suspicions.
That pipe has to be twice the diameter of the collector, or it will affect the exhaust engine.
I wonder how many people don't know that.
And you know, some engines, it's like nitrous engines. It's like you don't tune nitrous engines on the dyno. That's not what we do.
Okay.
Pro mod engines, they are tuned to a certain VE level. Because when you introduce 1,200 shot of nitrous to this thing, that's how you tune the mechanics and all the variables in the system. So you might have 12.5, 13 to 1 compression ratio.
Yeah.
You've got buku duration, huge amount of duration on the intake, 336 degrees of duration on the exhaust, smooth opening. Nothing about that engine is designed to run normally aspirated. So the data, the power figures and torque figures you get, you can only correlate that to how bad it burns up on the racetrack or how long it lives. I'm serious, dead serious. So we know, I knew, if a Pro Mod motor made over 1,800 horsepower, it would burn up on the racetrack. The VE was too high. It was too efficient. You're throwing in an oxygenated air-fuel mixture, not changing the compression. So your burn rate is super fast. It's, you know, where a turbo or a normally aspirated burn rate's like this, nitrous is like this, okay? It's instantaneous, and it has a lot of problems associated with that flame speed and a 5 1/4 bore. Okay, you got a big bore. If you have a Formula One engine with a 4-inch bore that only moves a piston up and down, your flame propagation, easy, especially with a center fire plug. Now you have a 5 1/4 bore with a plug that's offset from bore center, propagates 360 degrees out, and then starts moving across that combustion chamber, what is the pressure on the other side of that chamber by the time that flame reaches about halfway? It's freaking astronomical. And people wonder why that goes boom and instantly preignites and detonates over there. That's why. So Joel DeBus at Moose, the amount of effort and time it takes for them to study those combustion chambers and make changes, and coming out of the pro stock ranks, it was like, oh wow, we can run more compression and less nitrous. No, you can't. We can do this. No, you can't. It's a completely different world, completely different. And I'm not gonna say what Joel's doing or what we did, but what you think will work won't work. It won't work. If you approach a nitrous pro mod motor from a normally aspirated point of view, you have, well, it was 2 years worth of work, and we got our ass handed to us. You know, we burnt shit up right and left. And then you start thinking, well, wait a minute. The quench area is like this, and the compression, but the flame speed's faster and the compression lower, so the molecules are this far apart, and it's pre-igniting over here in a lean area. So what can I do with the air-fuel mixture to get more fuel over there? That's a big thing. What can I do to slow the flame front down? It's a huge thing. Yeah, in a normally aspirated engine, I always say we're trying to speed it up and get it done and burnt as quick and as fast and as perfect as we can. And in a nitrous engine, you do everything you can to slow it the frig down.
Yeah.
Because, and that's why early on in nitrous, you know, if you had a 9 or 10 degree cylinder head, you could not make that work with nitrous. You can now. There's certain ways to do it. In my personal opinion, you can make a lot of power. You can shove 1,000 to them. 1,200, it gets dicey. You have to have a lot of chamber surface area and volume, and then manipulate that to try to slow it down. But you also have your flame front trying to reach out across a 5 1/4 bore, and the lean areas in those chambers opposite the plug, they just eat it alive. And Joel and I were talking, he sent me a message the other day, and we were talking about things that I'd tried and he'd tried. He saw the same thing, and we ended up going the same direction and doing the same thing in order to counteract that. It was cool as hell. That's why I like talking to other people in the industry like myself that deal with this stuff. And in my day, it was all super secret, screw you, I ain't telling you anything. But it's not like that anymore. A lot of us collaborate together, and it's amazing how far we can go and how fast we can accelerate our own learning curves by comparing data. It's like, okay, well, Joel did this, saw this, and went that direction and fixed it. We did this exact thing. Well, that verifies that what I was doing was the correct path. Otherwise, I would have never known, well, maybe if I did it differently. But no, he chose that same path and saw the same results. So what I did was correct. I hate to get off track here. Man,
one of the things I heard last night at this meeting that Joel happened to be at and runs was that the horsepower now, 1 horsepower at this point in time for like pro stock stuff, it could be NASCAR, but I thought they were talking pro stock. It's $1 million a horsepower now. In
1990, I actually did a cost-benefit analysis and a time study. I actually did them about every 2 years at Brewer Morrison. And I actually projected the power increase per year. We were gaining 15, And when we saw the 60, 65 millimeters come in there, it almost went vertical. It was like 200 horsepower up top overnight, same torque. And I was like, oh God, if we're at this point, this graph's going, like this, and then it went, I'm like, oh boy, here we go. What was your question again? I got off track.
I was just mentioning, we'll do this. So Joel DuBois, he's a guy that I met through when I had Pat Musey on. We did a live chat with Pat, and I actually had hooked up with Joel on the backside. And Joel, I'll tell you, he's a wealth of information. Not because
Son
he's
of a bitch. He's right. I forgot about that.
Not because he works for Musey now and does all the cylinder head work. Everything that comes there that has cylinder heads done, Joel's hands are on it. But Joel didn't just do that. Joel's done NASCAR. Okay, he's done Indy. He's done everything that you can think of, Top Fuel, anything that there's out there. There's Pistons.
Let me tell you why there are no cylinder head development people like me and Joel in NASCAR right now. And Joel is probably one of the primary ones that you can blame for this.
I mean, I would say it's restrictive, and there's no R&D money.
Well, yeah, they wanted to restrict. They had to restrict it. And Joel was one of the causes for that. Because what he did and what he found and his development progression was making them spend millions of dollars. Because they didn't understand. The engineers didn't understand. They don't. The owners, the builders, the dyno, they don't understand what he was doing, how much power, more power he could make by designing the way the heads and the manifold and everything the way he did was not only the exact opposite of the way the engineers told him it should work. It was costing him $3 million every time he made a 10, 20 horsepower gain.
Right.
When you got 26 engines in rotation and you got to put new heads and manifold on those engines, it's millions. So people wonder why we only have like 3-4 engine builders in NASCAR. That's the reason. Because they were spending, what, 10 million a year? 20 million a year?
Yeah.
30 million? I don't know. Joel could probably tell you.
Oh, he could tell you.
But that was because people like me and the engine development guys were pushing the metallurgy and the ring packs and the heads and the valves and all this stuff. And every time they made a gain, it was like, oh shit, now, and then that leads to other problems. So who are you going to give that new engine and that new power to? You're supposed to be supplying these guys with an even playing field, and you just got 20 on this guy?
Right.
Well, that leads to a lot of pissed off people. So I understand why NASCAR, why Hendricks and Childress and these guys threw us all out and just want a cookie cutter engine and a cookie cutter car and leave it up to the driver. It's money. Money.
Driver. Pure
and simple.
So we might as well say this while we're here. Joel is an outstanding individual in all aspects of wealth of knowledge. So I'm actually going to have him on for a live chat. Him and I have talked about it, and I started planning about it. I didn't say anything to him yet. But we're going to have him on and do a live chat, like I've done with other guys, to kind of get some of his information and his knowledge. Because, I mean, what he has, and one of his main things that he wants to tell you guys, just like Darin is saying now, these guys, Darin and I are the same age. We're 60 years old. Joel's, I can't remember how old he is, it doesn't matter. The point is, these guys are dying. He lost all of his mentors in 1 year. This knowledge is going away. And if we don't save it and record it, and I put it somewhere on this YouTube channel where it can be accessed, when me and you are in 10 years, we'll be 70. You think we're going to be doing this? Well, we're going to be doing YouTube, that's for sure.
Passing this knowledge down, I've got a really, this story As a matter of fact, I was talking to Preston today. Preston Mosier,
Yep.
who runs the cylinder head department at Bischoff Engine Service.
Mm-hmm.
I work under him. Okay, I do what he tells me to do, and Tony tells me to do.
Right.
But we're a team. We work together, and the Buick cylinder head that came out in what, 89, 88?
Yeah.
Dart. Well, they canceled. They don't make them anymore. I think it's been 13, 15 years since they even cast any. Well, this guy has a Buick cylinder head. This engine is like 2 or 3 inches. I forget, but everything he has is around these Buick heads. He's like, man, can you just give me another set of Buick heads? Because I want my manifold to fit. I don't want to go to another head, because when you do that, that's a whole other engine.
Oh yeah.
That's 26 grand. So he shipped us his heads, and he found a raw set of Buicks. And by I say raw, it still had the risers on it. It's just a casting.
Yep.
There's no guides, there's no squaring, there's no nothing. So Preston took that cylinder head and dialed in the valve spacing, because they were all different. Dialed everything in, machined the whole thing up, and he had never ported a Buick before. Now, the Buicks, in their day, were killers, because they had what no other cylinder head had, and that was a 10-degree valve angle. A very small, fast burn combustion chamber. You could run 10 degrees less in that, and that'd be 25 horsepower in a high winding comp engine, like a 350 cubic inch motor.
Okay.
Probably making 750 horsepower back then. So they were a huge advantage. But the intake port on a Buick is aimed at bore center. It takes a completely different approach to port them. And that casting was, how do I put it, ill-equipped to handle the port that actually needed to go in there to actually move enough air per its valve size. It was a thin water jacket. It had bolts in the way. You couldn't shape it properly. You just couldn't get there. And I remember I brought this up today, by the way. It took me 10 years. And back then, comparative to what I know now, I was faking it, making it until I was faking it until I made it. You know what I mean?
Yeah, I get it.
I didn't know jack shit. So I'm porting these things out, and I'm getting 375 CFM, and everybody else is getting 370, 375. So I'm getting the airspeed, or the airflow, but I didn't know anything about airspeed. I made them too big. We put them in a B dragster. It was a dog. Shit, it was like 2/10 off of the competition.
Yeah.
It was just because I didn't know anything about managing the airspeeds in the system. So 10 years later, we were getting 400 CFM, and that's about it. I mean, that's it for a Buick. And to get that took everybody about 10 to 12 years to reach that point. So he gets this cylinder head, and he says, hey, you got any pointers? And I said, yeah, there's water right there. I know you want to kick the short side that way. I know you want to do it, but if you do it, you're going to go right into the water jacket. He's like, all right. So he did his port, and he was back and forth to the flow bench maybe for a day. His first port flowed 395 CFM when he was done. This is a guy who had never ported a Buick. That's how far the information, the level of information that we have now. And, I thought that was just so amazing. I looked at him, I says, it took me 10 years to do that. And you walked up here and go, boom.
Yeah.
Because he knows what we know, and he can apply it.
I'll just add on to that story. Joel told me a story. I'm pretty sure it was him. It might not have been, but it could have been Don Lucido. But I remember a story. One of them told me that they went to an IndyCar race where Buicks were racing in the Indy Series, and they kept blowing head gaskets. And I could be wrong, Joel, but he said he went down there, he looked at the whatever, the block, the head, whatever. He said he made a couple, told the engineer, you got to do this, this, and this. They did it, solved the head gasket problem.
I wonder if he was the originator of the bolts that go down on the ends.
Yeah, something like that. Yeah.
Because the first time I saw that, I went, oh, yeah. You know, it doesn't matter how old you are or how long you've been in this business. It's, you see things and you're like, why didn't I think of that? That's so goddamn simple. But guys like Joel, you know.
So we could touch on this. We might as well. We put the question up there. But Joel says, also, when you're dynoing, seal off drains in the room. Dyno cells have a negative pressure in the room that draws sewer gases, which is a NASCAR thing. He told me that they had a problem with that. It was drawing the sewer gases into the carb, you know, into the intake system through the pipe or something.
And how many people plot the pressure drop in the room? Because if you've got a dyno where you can't open the door when the fans are on, that's a problem.
Okay.
I mean, you're drawing a negative pressure in the room. It should be relative to the barometer. Are you mounting the air temp in the same place relative to the airstream coming in every time?
I know he's down. He's at home talking away, trying to tell you what's going on.
And a matter of fact, we were going to have Adger in here, but he was going to tell some cheating stories. Couldn't get together on camera, but
yeah.
You know, one of the things was, if you know and understand the variable and the calibration involved for that dyno, well, that's something you can manipulate, like the air temperature sensor and the humidity, the read vapor pressure. So if you have a 70-degree inlet temp and you put that in a hotter spot,
sure,
well, that's more correction factor. Well, the EM guys, the engine master guys, were actually testing that on their dyno. It's like, I have this hood scoop, this plate on the engine or whatever. Well, I'm going to turn it over and put it underneath. Now it's going to be picking up the hot air that's coming on the back of the engine. I'm going to get 5 horsepower. If you give a drag racer a rule book, he's going to go through that with a fine-tooth comb, and he's going to find a way where it says that doesn't say that's not cheating, but that's power.
Right.
And he's going to use it.
Which is kind of bringing up, since we're talking about this, the exhaust factor. Tom says, hey, Darin, the dyno exhaust systems hold a column of air. You're touching on this question as I type. The exhaust pulse has to push the air in the pipe out of the way. The air mass contained in the
in the system itself, and he's correct, but that's why I say it has to be twice the diameter, because anytime you have a pipe with some harmonic content and you double that width, it's better to go more than double, but twice its width is the minimum where it actually thinks it's seeing atmosphere. Now the length of that column, and whether you have silencers or it goes out the back of the building, yeah, I could see how that would affect it. Absolutely.
I think this is what he was put. He can only.
It's not going to generate any negative harmonic content because it's twice the size. It's dissipated.
Let me add this to it, because this looks like the other half of the question, because he stopped there with a hyphen. Part 2, pipe must be pushed out of the way. Same with mufflers. So how do you prefer to dyno as regard to exhaust? See previous part of this question.
You know, that is so difficult for engine builders to manage when it comes to dynoing an engine. And it's not an afterthought. It's not something that is disregarded as, just bolt those headers on there. No, there's a lot of thought process there. But we need to dyno the headers that you use on the racetrack, and we need to hook them up and evac them properly.
Right.
But that's not always possible. Sometimes you have like a truck puller. The headers are straight up and down. So are you going to pipe that out? Sometimes you have zoomies. What are you going to do with zoomies? If you put a header on there and you try to tune that thing, you're going to be so far off. You're going to be out in left field. So that's a difficult thing to manage for any engine builder. I mean, you can't have 2,000 sets of headers and 4 evac points. And
now, Jacob says, technically, would you want your exhaust at the same atmospheric pressure as the intake?
I would want it the same. Whatever the ambient pressure is, that's what it should be. Whatever the barometer reads, that's what it should be.
Okay. Now, I saw a short or reel on Facebook today, and it was some comp dragster, and the guy was talking about how he doesn't use a vacuum pump when they dyno an engine because it starves the oil away from the wrist pins. I mean, we know it does pull that and lower the oil pressure.
Well, yeah. As a matter of fact, we used to burn wrist pins up because when you're pulling 20 inches, that mist, that vapor mist that normally oils the wrist pins is gone. There is none. So unless you have actual piston oilers or pin oilers shooting an oil stream in there, which you don't want to do because that's drag, and you're loading up the oil rings. So yes, as a matter of fact, I saw a video the other day. We might be talking about the same thing. He was talking about breaking the engine in without the vacuum pump. And use break-in oil, not full synthetic. Because it has more sulfur content. It'll let those rings. The whole idea behind break-in. I use that term very loosely. Break-in in the 90s is completely different now. I mean, for high-end engines, after 3 pulls, if it doesn't have ring seal, you missed the boat. Something's wrong. Tear it down because you did something wrong. I mean, that's how good the rings are now. Break-in procedure back in 95, 8, even into the 2002, 3, 4 would be getting the piston and ring grooves, having a $25,000 setup that cuts those grooves with a micro cutter within 7/10 millionths of an inch, and leaving them 4/10 clearance, beating the engine, getting some heat in it, getting the deformation out of the piston. The exhaust side's hotter. The piston's going to change in shape a little bit. Taking it back out, cutting the bottom of that ring groove. That's 8 horsepower on the average. Well, now you don't have to do that. We had to break our pistons in. That was what? Doing the rings. I mean, most people have no concept. I mean, just the rings themselves. You would take the rings out of the box. You'd have 5,600 rings. You'd light check them. You'd end up at 20% of that. Then you would hand lap them. You would have an apparatus that held the ring in the lathe. You would back cut them. And by the way, that chamfer on the back of the ring, rings aren't flat. They're tweaked up. So when the cylinder pressure hits them, they go flat. When you back cut them, you take that out. And when you lap them, you take that out. So now the ring's flat. So when the cylinder pressure hits it, it would do this. So now you have to put that groove back in there to tweak the ring back up. That's what we used to have to do to get back cut rings. We have to do it ourselves because they didn't make it. And then Matt Hartford, brilliant engineer, worked with Total Seal, and they just went to town. Man, they spent at least $10 million, probably more. And now they have these huge machines that sit there and lap these rings to within millions. So when you put a ring in an engine, you really have no idea the amount of technology that went into that. So, and reduction in friction power. Total Seal is responsible for 30 horsepower right now in a Pro Stock engine.
Okay, just on ring design.
Yep. Reduction in friction power. Active. The rings, you'll be able to reduce the radial Instead of 175, you're 140, 145. So, and you're 26,000 stick. Well, what that ring is just, for a gas-operated ring, it's bang, instantaneous. I mean, those gas ports will throw it out. So your ring reaction time is much faster. So you seal it up quicker, trapping more. And the wool, the actual barrel face has such a small unit loading area as opposed to what it used to be. That's 25, 30 horsepower.
Wow.
And they seat up immediately. You don't have, you know, when you have a ring with a gap and you push that gap together, the ring forms a football shape if it's not made correctly. So you're taking a round ring, compressing it into an oval. Well, when you compress it and put that, it should be round. And now they have that. That's why you have 5,600 rings and threw 80% of them away, because you were light checking them. You were checking them with a light to see if you could see light around them, or they footballed, is what we say.
Right.
And you measure your free gap, the metallurgy, the metal that the rings are made out of nowadays. I mean, we're using tool steel, stainless. They're working on an Inconel top ring to be able to handle the heat.
Yeah.
Before, what you would do is the ring just relaxed on the table. You would measure its free gap. Okay, that was documented in the build sheet. You put it in the engine. You ran the engine. When you took it out, if that cylinder, gap would decrease relative to the heat that ring saw in that cylinder. So you would say, okay, well, number 6, which is usually a problem in a lot of big block Chevys, had a free gap of 350, and now it's relaxed at 200, and the rest are 250. Well, that ring just got yielded by the heat and lost its tension. You don't have to really, you still have to measure that. That's still something you have to know and quantify and document, but it's a lot less. You have a lot less variation and a lot less collapse. As a matter of fact, Joel and I were talking about this on nitrous stuff. You'll have a tool steel ring, and let's say you detonate the engine a little bit, you rattle the shit out of it, you throw all that heat into the ring, and it kind of goes out of whack. And you measure the leak down, and it's like 60%. It's like crap. So you make another ring, you make another run with a good tune, and it comes back 40%. Because now you've thrown more heat into the ring, and it's relaxed and conformed to the cylinder. I saw that a lot.
Scott Foxwell says, consistency and repeatability are king. The actual numbers are really secondary.
If you're chasing accuracy, you'll chase it till the day you die. Chase consistency and repeatability, and you can learn something and move ahead.
Funny thing is, if you're on my side of the page, what do we want to see? We want to see dyno numbers and torque. We want to see this so we can tell everybody, you know. Don Dotterer says, I remember Darin and Joe Mondello did a presentation at UNOH. It was awesome. During the Engine Masters Challenge, there was not enough air going through the room.
Yeah, as a matter of fact, that was something Adger was going to talk about.
We're going to get him back. We'll have to figure out what the deal is, if he needs whatever. We'll figure that part out, because that's just something that I think people would love to hear. I mean, we've had like 120 to 130 people attending this, and it's great. So it'll be a good review. John Salvatore says, SAE has a textbook on how to design a dyno room. It's an expensive undertaking.
My brother, when he was younger, before he got into engines, 16, 17 years old, was framing houses. And he has personally built 2 dyno rooms that I know of from the ground up.
Really?
Yeah.
Greg says, I had the same damn problem with a sealed hood in 2010. I was chasing my tail for a year trying to figure out why all I could do was pick up or lose
torque. And the power was like...
But the motor would never make more than a something.
Yeah, and it was unresponsive. That's another sign. Anytime anytime you have an unresponsive engine, get to the bottom of the problem because you have a problem. If you can move the cam and the timing, this thing just won't respond. I mean, you move the timing 5 degrees, you should see a change.
Well, hell yeah.
And if you don't see a change, something's wrong.
Okay.
Engines should be reactive to change if they're tuned well.
A freaking year, though. That's crazy. Sorry, Greg. I wish we would have had this earlier.
And that's one thing. Big ports that are way too big. That's exactly what they'll do. Yeah, the engine just has a governor on it. That's all the power it'll make. It's all the fuel it'll pull, no matter what you do.
Member for 7 months. Thank you for joining the membership. We appreciate you. If you were to buy a new dyno from a manufacturer, what dyno would you buy for your own dyno cell? Whew.
Well, to tell you the truth, I don't like any of them.
All right, pick one that you kind of like. I mean, there's only a few to choose from, right?
The DTS platform, I think, is a little better. I think it's more workable, tunable, consistent. Now, when DTS first came out, before Superflow bought them out, I like their absorber. You know, different absorbers. The Dyno controlled inlet water, the Superflow controls outlet water. There's a difference right there, just in the way it accelerates and handles a load. The DTS originally had a proprietary software, and a lot of people converted them over to DPAC. I love the DPAC data acquisition system. It's simple, repeatable, but it has all the math, everything you could do to custom tune it to what you're doing. Some dynos are very errant. What's the word I'm looking for? Difficult to maintain consistency, but not only that, I like things simple. If you have something where you can control 10, 20 different variables, not 150.
Right.
You know, it's like Superflow 902 dynos. They can run digital, they can run analog, they can run with filter. There's filters. If you go to one dyno that has a filter rate of 7 and it's a looping average, and then you have a column average at 3, it'll come on the torque curve different, it'll have different torque readings, the power band will narrow or widen. It can do all sorts of things just between two 902 dynos. If you heavily filter your dyno data, that's not a good thing either, because you want to see the reactivity. You want to see what that engine's doing. And if it's going up there and spiking, I want to see that.
Right.
Don't filter that out. That's something I can use to diagnose what's going on. And a lot of these dynos now are just so heavily filtered. They want that nice smooth curve. Another thing is static pulls and extrapolating a curve. That's the dumbest thing you could possibly do with a drag race engine. In other words, you take the engine to 5,000, you get a power reading 6,000, you get a power reading 7, and then you just extrapolate that curve. Well, that's not an accelerative curve. It doesn't tell you what the fuel curve, fuel delivery actually needs to be in an accelerative state, which is actually the way you use the engine. You know, static pulling is how we did it in the 60s and 70s. That's
What's BS use? What do they have for dynos?
902s.
Okay.
Yeah, and even those dynos, I mean, I think there's 8 horsepower difference between the two.
Is there?
Calibrated exactly the same, same filter rates, same everything. And the more electronics you have, and the DTS stuff was all analog, and you can run the Superflows in analog or digital. I preferred to run them in analog because they were less susceptible to RF. If you have an RF problem, you can have, as a matter of fact, we had a problem. We had the neutral and the ground plane on the building was crossed, and it was back feeding about 2 volts, 5 volts back into the ground.
Really?
And digital, it can't put up with that shit.
Right.
So, and then the RF, the radio frequency interference from coils and what have you, if you were too close to the box, you'd be at 8,000 RPM full load, and the dyno would just release the engine and go against the limiter, and you're just, it took us 6 months to get to the bottom of that. They've worked out a lot of those problems over the years, but RF interference with digital data acquisition is definitely something, routing to, if you're routing a low 5-volt signal wire next to a high voltage, you're going to have problems. Actually, I went to the extent of trying to build a Faraday cage around the damn box.
So Andy from Unity Motorsports Garage, he says, plenum volume for power on the dyno versus what accelerates best of the track can be completely different. He learned that the hard way.
Hands
Big
down,
difference.
100%.
Yep.
As a matter of fact, you can tune power, racetrack power, right out of the engine on the dyno, because bigger plenums, because you're controlling the acceleration rate, the dynamics of the engine, the load curve relative to each gear on the racetrack versus the dyno is 2 different worlds.
Way different.
In the carburetor days, we had dyno carburetors and race carburetors.
Yep.
We had dyno headers and race headers. We had, a lot of that stuff changed. And we actually got into routines. We found that the engine wanted to advance the cam 1.5 degrees on the racetrack relative to the dyno. And it wanted 2 degrees less on the racetrack than it wanted on the dyno.
Okay.
Well, why is that? The load curve is different. The chamber temperature is different. By the time you hit high gear, and you are actually in that 600 RPMs per second acceleration range, the chamber heat is up there. So now your detonation sensitivity is really, really high. So that's not something. And the acceleration rate of the plenum. You can't stall a plenum. On a dyno at a given acceleration rate, you can have this huge plenum.
Right.
And it will compensate. It will make it accelerate at 600 RPMs per second.
Right.
And you won't see that change. You can see it a little bit in the fuel curve. And I always say, if your fuel drops, it's a losing game. How much fuel? Look at the fuel curve. And so on the dyno, you can put big plenums, spacers. You can stack those spacers up. You can put bigger carburetors, bigger everything, and it will show more power. And then you shift and you go through the front window because the thing stalls. You can't kill the momentum of the air. When you get that system moving, when that airflow is moving, and you have 4 valves open at any given time. So what we see mathematically, dynamically as an open and stop and start system, to us is a constant flow system because it's happening so fast. And on a plenum, if it's too big, especially with carburetors, and you drop at 1200 RPM, and now it takes time, that big plenum has to re-accelerate. Well, that's lag.
And that's time. That's seconds off your ET right there. Now this is kind of interesting. CD says, CD Burlock, 2 engines make same numbers. Does the one using more fuel a better engine?
What we used to call choke it on the fuel. If you have 2 engines, let's say they're both moving 530 pounds an hour, both making the same power, and you put a bigger jet in there and it's pulling 540, and one engine loses power and the other doesn't, the one that doesn't will be able to handle more load on the racetrack. An engine's ability to pull fuel and dynamic recovery after a shift is directly proportional to how much load it can pull and how fast it can accelerate that load.
There you go, CD. Now I know you're going to go through that information and come up with another question.
Now, choking on the fuel, meaning if you put 10 pounds per hour in it and the power doesn't go down, if you put 10 pounds an hour in it and the power goes down on one engine and it doesn't on the other, well, there you go. The one that didn't choke on the fuel is going to handle more load.
There it is. Greg says, I know of a certain big name engine builder that had 85 pounds of torque when the motor wasn't even running. I know for sure that I know both of the happy dynos, SS and SL.
Yeah, I know. You're right.
We don't know who they are. Thank you. Anonymous.
Yeah, as a matter of fact, those are the two. Those are the two.
Now, Ben Almeida, he has his own YouTube channel. He's been building engines for a long time. He actually worked for the Los Angeles County, I think, Sheriff's Department or Police Department as their mechanic there for a long time. Built a lot of motors. He says he is correct about tuning nitrous on the dyno. Had issues with plug readings and noticed the guy shut off the throttle and the nitrous guy controlling the button was a tad late and plug looked strange. There you go. Thank you, Ben.
Dyno on the bottle, I mean, that, I don't, it can't give good data. It can help. And now if it's a hub dyno, yeah, by all means. But because that's more relative to the load curves that you see on the racetrack.
Yeah.
But on a water absorber dyno, I don't think it can still tell you things. It can still tell you, the detonation sensitivity of the chamber and certain things, especially if you correlate the data you see on the dyno. If you dyno the engine, just send it to the racetrack, you're not going to learn anything. You dyno the engine, you tear it apart. You look at the burn signature in the combustion chamber and relative, and then you dyno it or you take it to the racetrack and tear it apart. Is it the same? Well, if it's the same, then the data you're seeing and the detonation sensitivity or the timing changes or camshaft changes is probably a lot more relative, but that's not always the case.
And that'll be a good thing for Joel. I mean, that's what he does. With Pat Musey, he's the man to talk to about that. So we'll get him on here and he can give us a little insight on that. Joel. Ricky Smith just lost in the final round, nitrous versus ProCharger. I'll tell you.
Racing dissimilar combinations is such a waste of freaking time. It really is.
Pat Musey told me, he said, you know what? Nitrous cannot compete with a ProCharger.
No, it's two completely different power curves.
Yeah, he says no matter what. Maybe early in the day, but once the heat comes in.
Nitrous cars should race nitrous cars, and supercharged cars should race supercharged cars, and turbo cars should race turbo cars.
There you go. I don't know this question. We'll see. Eric says, Darin, your brother that worked with you, is he an electrical engineer?
No, not the one that worked with me. Brad Morgan, my brother, has been the head engine builder at Roe Morrison for 30-some years. 30 years. My other brother, Larry Morgan Jr., is the electrical engineer. He works designing oscilloscopes and stuff like that.
Terry says, hey, Tim, we had a guy that hung out at the shop, and some of the guys said he didn't know that much and made fun of him, but now he works for NASCAR. Okay. Now, I don't know. Jeff's he's a member of a membership. 10-degree killer small block Chevy head. Not sure what that's in relation to.
The Buick. I think he's referring to the Buick.
Oh, yeah.
Everything stayed right there. I mean, they hit the nail on the head. 9.5 to 10 degrees is pretty much standard for unlimited NA engines.
And then he says this, symmetrical port. Is that? Yep.
Asymmetric ports. If you look at the Australian Pro Stock head, which the series we're doing, the member series for the Australian Pro Stock engine design deal, we're going through. The next video will be on the actual port, and it will be everything I know about designing those things. And Dart came out with the Little Chief, which was an asymmetrical head.
Okay.
And the first thing everybody did was chop the head up and move the thing over and make it symmetrical. And then Carl Foltz based his SBX head on that. And then I based my Airstrike head, Australian Pro Strike head, on that. So asymmetric heads are just a pain. And I don't know why he did that, but I suspect he did that because, you know, the Big Chief stuff was all asymmetric stuff. And, you know, if you know anything about the X pattern and the blocks, you can move the board, get everything straight, which is a problem with standard lifter board layouts and big block Chevys, because you have a lot of push rod angle on one of those, and one of those will lose 35 thousandths of lift just in deflection, because you have a rocker arm like this, and you have a push rod that's sideways. So as it opens, it's moving the rocker arm like this.
Right.
So the push rod's running away, and that causes all sorts of other dynamic problems. Symmetrical port is the only way to go.
Bill Ferretti, Darin, you seem to be impressed by the mention of the old school Heenan Fraud dyno. We had mid-70s pro stock engines on this type of dyno. I recall results at 1,000 horsepower capacity. HF dyno, explain please.
Those were the Cadillac of dynos, as far as they would take a lot of abuse. A Superflow, you couldn't run an engine 24 hours on. A Heated Fruit, you could. And I don't know anything about their data acquisition system, but everybody I've ever heard that dynoed on a Heated Fruit loved them. And I got to see a couple of them in the NASCAR days, and every guy that dynoed on those things absolutely just loved the things. They're consistent. I don't even know what data acquisition system they used, actually.
I mean, it sounds like any manufacturer would be using those type of dynos, you know, in a dyno cell where they have, you know, 10 of them in a row or something.
You're talking about $1 million dyno rooms.
Yeah. Alan says, thank you for your time and dedication to engine and head development. Have you ever worked with Robert Fulco on any projects? He has been a great teacher of me. Thank you, Alan. Nothing?
Nope.
Oh, okay. I thought you were thinking. I didn't see any smoke coming out of your ears. Smash the like. You know what, guys? Yeah, hit the like button. 136 people up there. Hit the damn like button. It doesn't cost anything. Go ahead. And I put this on a replay too. So if you got buddies that want to watch it, or you want to go back and watch it at your own leisure, where you're not sitting here watching us go back and forth, and you can stop it. It's on replay. So appreciate that. Love the knowledge of Tim and Darin and the ones following too, like you, Ben. Yeah, thank you. You know, when you got people like Joel DuBois, Ben Alameda, Scott Foxwell, I mean, these are guys that are in the industry. And when they come here to watch a presentation and to learn, I mean, it's impressive. That makes me feel good that we got a good job. We're doing something good for people. So thank you.
You know, Joel and I met when we were introduced to each other by Harold Bettis, because Harold said,
yeah,
you two kids get together and meet. Now, we only met once, and I think I was 20.
Met who?
Joel.
Oh, okay.
We were kids. CD
says, I admire Darin and the others with extensive background racing, not just dyno flow and testing. Big, that's it. That says a lot right there. You know, I don't know how many guys have got the experience. You know, they may port heads, but how many have done, you know, worked on the Wright Brothers airplane, or worked on an airplane engine, or worked on a boat? You know what I mean? That's 40 years of experience Darin has. I always pump that up.
I always say I don't care if it's a Briggs, a Stratton, or Bugatti. If it's got pistons that go up and down and crank that goes round and round, I'm all there.
That's it.
If you want to shove it to extremes, that's...
Tom says, Darin, have you ever tried back-to-back dyno testing with engines honed and valve seats machined at running temperatures, as well as valves refaced at running temp?
So you're probably talking about hot honing and yeah, hot valve jobs and all that stuff. Torque plate valve jobs. For a drag race application, it was a complete waste of time and didn't yield any positive results whatsoever. And I think the major reason for that is short run times, larger clearances, and the loading as far as if you're off a little bit on the valve seat or whatever, that thing is going to beat out. I mean, it's extreme. But when you have to machine something for endurance that has to last 1,000 times longer than a drag hit does, like in NASCAR, that's where stuff like this can pay dividends. And I played with torque plate valve jobs and all that stuff. What we did was, did it yield power? Really couldn't see it. What we do now is just develop, machine, and produce the cylinder heads so they have the least amount of instilled stress in the casting. So once they move, they'll take a set and they won't. Let's say if you drive your seats in cold, you have too much press, your interlock's off, the valve seat materials are incompatible, iron and whatever. Yeah, what's going to happen is you thermally cycle that engine and the valve seats just keep moving and moving and moving and moving. And guides, too. You can have that with a guide if you don't have enough support or enough surface area to hold the guide in there correctly. There's a lot of things that can happen, but through the decades, we know, okay, well, I put 8 to 10 thousandths press on the exhaust. I use 6 thousandths on the intake, especially if they're interlocked, and 500 deep. For a 375, I go up to 8. So I want to instill a little stress in there as you can. And then you have them taken to 250. You quench the damn things a couple of times. You're going to get the initial stress out of there, and then you do your valve job. Is it going to move? Yeah, it's going to move. They all move. But it's going to move a lot less. And when you come back in and do the second valve job, it should be stable. But if you do it wrong, it'll move and move and move and just keep moving.
I'll tell you, last night we were at that meeting. I was at that Zoom meeting with Joel, and there's another gentleman there. I don't know who's he's affiliated, but he's got a lot of experience building engines in NASCAR and Pro Stock. Now, he said last night that hot honing used to be the big deal, 90 degrees Fahrenheit. They used to do all that. He said right now, he says he's been through all the NASCAR shops recently. He said he hasn't seen any hot honing going on at all.
No,
None.
Nobody uses it anymore.
So whether it was a fad at that time.
It was an avenue that we pursued, like many others, to try to get a handle on consistency and ring seal. Ring seal was a battle. In 90 and the early 2000s, it was a battle. I mean, I can't count how many times you'd have to drop a piston and put a top ring in some hole because that hole, lost ring seal.
Pontiac 411, thanks for being here. We appreciate you being here, because you know what? We're not racist. We don't care if it's a Ford, a Chevy, a Mopar, AMC. I don't really care. They're all, like Darin said, anything with a piston I like. People are always saying, oh my God, it's Ford is this, Ford is that, Chevy. I don't really care about. I don't get involved with those arguments because in this type of environment with a YouTube channel, if you stay focused at one thing, like I'm a Ford guy, hey, that's how it is. you're going to lose out on a lot of different views, a lot of different venues, a lot of different information, because that's what this is about, sharing information and education. And it doesn't matter what you race or what you like. You can pick something up here.
We have the technology, the machining capabilities now to make anything we want. And by the way, that's the way this industry is going to go. The aftermarket is no longer developing new products the way they were. So
there's no R&D.
We have to do it ourselves.
Yeah.
So now you have, you know, Visner and these guys. You know, I want a 4600 bore space small block with a Ford bolt pattern, except add these bolts here with the Chevy main and a 65. There's no brand associated with that anymore. It's just specs.
Well, thank you. We appreciate you being here. This is one of those questions. I'll put it up, but I don't know if we're going to be able to answer it. The guys from Argentina, thank you for showing up here. The question is, should the short side of the port be narrower than the long side in a high port with more than 80% line of sight?
Flip that. The short side should be wider than the roof. So,
you got that? Brain. I don't know if that's your name, but we're just going to call you 7098.
So basically, what you're shooting for is a short side, and that's blue. Let's do something else here.
Get white.
Yeah. So basically, what you're shooting for, if I can do this.
See, and this is the thing, guys. This is where, you know, we're kind of stopping what we're talking about Dynos to answer someone's question, because this is an open chat. And if we can do that, we're going to try to accommodate everybody. You know, time isn't really the limiting factor during these live chats. I've come to notice. But some people ask questions about.
So if you have a square short side, the airflow is lower up here. And on the Australian Pro Stock port design deal, I'll go into the velocity gradients and the velocity mapping all the way through the port. But usually at the short side apex, right when it turns, you'll have a gradient of maybe 60, 70%. So it'll be 220 feet per second here and 380 down here.
Okay.
And on an Australian Pro Stock, it'll be 350 and 290 something. So it's a lot less. But so what you want to do is get that higher. So you fill those in. And you want to get that lower, so you make that wider.
Got it.
That's the shape.
That's the shape.
This is the shape.
You can't see. Bring it over this way. You can't see it. You know what? Let me get out of here. You just yell back. Hang on.
So if you have a square, dang it. Okay, if you have a square, these corners are dead, and you got 220 up there. Say 350 down here. So let's say 380 down here. You want to slow that down to 350. You want to bring that up as close to 300 as you can. You want to narrow that. So bring that down, make the area bigger, and make that smaller up there. Round your corners on your roof and widen it at the floor. That's the way all the ports we do are.
And that's kind of like the basic port shape that you had talked about. We won't get into it now, but as far as like the revelation to you, how to shape that port. You know what I mean?
And like a small block Chevy, you know, it's got a straight wall, and then the short side.
Yeah.
Well, I want this wider than the roof, but I can't do anything with that wall because it'll actually hurt the airflow. So what we do is this. The push rod wall comes around and then leans in to shrink the roof.
Got it.
Get the airspeed up at the roof.
But I don't know if you heard me, but I was saying that's the generalized shape that you talk about, that you kind of base all your ports at. Remember what we talked about? I won't get into it now, but that shape, you keep that in your mind's eye.
The NASA tech brief.
Yep.
In 69? They knew this in 1969. This is the most aerodynamic shape you could possibly have.
Let me put you back on full, so all right, because that's hard for these guys to appreciate.
When you're turning a corner and you don't want to make it bigger to slow the air down in order to navigate that corner, the most aerodynamic shape in the world is this. That's, kind of sucks, but see if I can get it a little better. Yeah, it's a little better. But basically, what you're doing is, if you had a square port, now when the air goes over the corners, there's vortex generation in each corner. And the airflow is really low up top. So your actual velocity map will look like this. The airspeed is really concentrated in the center or closer to wherever bore center is. So you want to make that wider. This is why the airspeed is so high, one of the reasons. So anything we can do to... And a lot of my ports, if you look down the port, you'll see the short side come in and go like this in the bowl. And the short side will be like this. You'll actually see it come out and it forms wings that reach out into the bowl. Because if you just have a short side that's square, that minimizes your area. If you can lean it back and make it wider right there, make it wider down at its base, it gives it more area to navigate the turn. It'll even everything out. Well, a lot of times. Now on a small block Chevy, you have to kind of do that regardless, even if you have to run it too big. Yeah, I'm going to get into that in the port design deal.
Okay.
The lower the port gets, the bigger the areas have to get in order to navigate the turn, which is why all the ports have been raised up. If you get it the proper angle of attack, the airspeed's even up, and you could run it at a higher airspeed without losing, or without it hitting the Mach limit and really nosing over. It'll hang on a lot further.
All right, 7098. So that means you need to be a member.
80% line of sight. Yeah, as a matter of fact, that's kind of... Preston and I were talking about this many weeks ago, and he's like, I hate that, saying line of sight, because it makes it sound too simple.
Right.
And he's right. It makes it sound too simple. But yeah, in something that's going to wind up, you need to see about 80% of the valve. That's a true statement.
Don't forget, join our membership, 7098. C. Stavros says, Gail Banks has a 300,000 AVL dyno. Okay.
And talk about keeping track of your variables.
Yeah.
And AVL dyno keeps track of everything.
Ty says, so if dyno numbers are mostly proprietary, are they basically useless as advertising? Is the only real value as a measurement of each change between tests on the same dyno, like my flow bench test?
If the dyno numbers are mostly proprietary, are they basically useless as advertising? Yeah, pretty much. You have to look at, and it's like when people say, well, we built this small block Chevy and it ran great. Great compared to what?
Right.
Horsepower per cubic inch, torque per cubic inch, engine speed, or relative to the pack. You have to have something to base and judge that off. So if somebody is advertising a power figure and his guy's out front and the other guy's has the same power figure and he's sucking hind tit in the 16th spot, well, you can make your own determination.
Blame it on the driver. There's someone, thank you. Thank you for welcoming him back in. Let's see what this, he says what? Basically, we could call this episode, why do dyno numbers are mostly BS? Good.
Mostly, just like flow figures.
You can make them whatever you want.
I mean, just flow benches. That's why I have 8 scientifically standardized calibrated orifices. And if I go to another shop, I run them across their flow bench. I note the difference in the curve. That way I can go back to my numbers, just like a dyno. If I've worked on that dyno for 10, 20, 30 years, I know that like the back of my hand. I know exactly what that engine should do. And if I make a gain or a loss, I can equate that directly. But if I go to somebody else's dyno that's unknown, those numbers don't mean a whole lot.
Right.
And
how come nobody makes full runs on a dyno? We have hub dynos that can do it. How come we don't have engine dynos that can?
There are dynos that can do it. All the Formula One dynos do it. As a matter of fact, they take the track data, plug it into the dyno, and the dyno runs the engine through the course. They actually tune the engine to the course they're going to run. Water brake dynos, those are eddy currents, but water brake dynos, you have to realize that if you have a column of water that's moving and you shut it off, the hydrodynamic pressure is ungodly. As a matter of fact, there's a couple of guys that learned that the hard way that blew up their systems.
Wow.
Because it's easy to have this, let's say it's a 2.5-inch pipe that's 6 feet long. You've got that water going, I don't know, 100 feet per second with this valve, and you want to drag the engine down and release it and stop that water. The hydrodynamic pressure just is it up like a clogged shotgun barrel. Looks like, you know, in a cartoon when they used to blow that's exactly what it looks like. It just, the head pressure, the water hammer effect is unbelievable.
Thunderbird 1968. I love those cars. Hey, first time on the live chat. Glad you guys got your channel back. You're damn right we were glad. Thank you. Yes, appreciate that. Greg says, Roy Johnson told me don't play with Punham spacers on the dyno. Only do that shit at the track on test day.
Absolutely.
Okay, Roy Johnson.
Yeah, I got a lot of respect for Roy, man. Those guys did more with a lot less than most people.
Ed's Machine. Darin, what do you think about your dyno upgrades? I see a lot of people upgrading their systems to your dyno.
To my, like, Superflow, or like what my dyno?
Dyno 2, I don't know.
BES's dyno?
Throw it down there, Ed, if you're still here, and we'll come back to that.
Are you talking about the air system, or?
I don't know. What other dyno do you have? BS, right? You don't have one in your backyard.
Yeah, BS.
Okay, let's see. Ed says, torque is the reality number, and horsepower is a theoretical based on formulas and data? Question mark.
Torque is the real number. That's what a dyno measures. The strain gauge measures torque, period.
Yep.
Everything else is mathematical.
There it is.
Mathematically calculated.
I don't think people really know that. I don't think they get that.
I mean, the only readings you get are the fuel turbines and the torque, the force. You're measuring force relative to engine speed.
Thunderbird 68. So this is where the actual engine builders hang out. Good to know. I appreciate all you gentlemen's videos on porting. I'm enjoying doing extensive porting on my 68 429 heads. Well, then you better join the membership if you want to get all the details.
And the 429 heads are really thin in a lot of places. You got to be real careful. There's some truck pulling classes that mandate the use of that head.
Yeah.
And, you know, on a 436 cubic inch motor turning it, I think it's about 8,800. We got 900 horsepower out of those things. The stock heads.
Stock iron head.
Stock iron.
Damn.
429 head. Yeah.
Wow. How big was the engine?
It's 4.
Doesn't matter. 4 something is in the relative ballpark. It's not.
It might have been 450. It's a truck pull class.
Yeah. Yeah.
So
So
they mandate iron heads, and a lot of the old rules that govern truck pulling and even NHRA, IHRA, whatever racing were based off of those OEM factory heads. And in the rule book, they said, well, you have to use, you know, this cylinder head for that engine combination. Well, the problem with that is you I moved the camera, didn't I?
I don't know what he's talking about. What? Anyways.
You can't find the damn things anymore. I mean, all these super stock racers are scrounging the planet for these old OEM iron heads.
Yeah.
So that's why you see in super stock, they're okay, you can use this Edelbrock aluminum head now.
Okay.
It still has to have the same port volume, same chamber volume, and stuff like that. But
well, it may benefit you from joining the channel because I'll tell you, I do a lot of I got to get on those. A lot of the porting videos that you did with the 16-degree Chevy at APD, all the techniques. So there's a lot to learn there. Appreciate.
I remember porting a set of 455 SD heads in 1992, and back
Pontiac?
then.
Is that what you said? Pontiac?
Huh? Yeah, Pontiac 455 SD.
Yep.
And back then, just to get your hands on it was like $3,000 a set.
Jesus.
And then you're going to take them right to the edge and make eggshells out of the damn things.
Set on kill.
Yeah, Don Kennedy's heads. Yeah.
Crouchy from Australia. Congratulations on getting your YouTube channel back. Thank you.
Yeah, it was a little dicey there for a while.
Oh, you have no idea, dude. It was like I was ready to pull my hair out. I
thought they were just going to say, screw you, start it over. And I'm like, man.
Well, I won't get into it. It's a constant back and forth. Pontiac 411 in the house. He says, if you're trying to equalize distribution and one cylinder is rich, would you want to increase or decrease the size or velocity of that runner?
Okay. I would look at the manifolding first before I started playing with the air speeds.
Yeah.
If it's a manifold distribution issue, there are a lot of ways to skin that cat. Fuel dams, fuel grooves. Yeah,
Spacer.
you can change the airspeed in that runner. I would rather try to get the fuel distribution even in the manifold.
Right.
If it's a manifold issue, which I'm sure it is.
Mm-hmm.
But, and it depends too, because if it's a Ford, it's got long runners on the outside, short on the inner, and you have to run the outside ones bigger than the insides. So there you have that velocity difference. The insides are usually faster. Yeah, it just depends on the engine, but I would try to figure out what the fuel distribution is and try to get the fuel in the runner that is lean other ways before I would play with the airspeed.
I mean, how are you going to know though if is it the manifold or is it the carburetor or combination of both?
Or
right?
carburetor mounting. Yeah, it could be a plethora of different issues.
Yep.
Get to the bottom of that first, why that issue is raising its ugly head, and then address what you're going to do.
So he's got another question. I don't know if this ties in, but we'll jump to this. I've always been a GM guy, but Ford seems to be ahead of the game on head design early on. Not sure what you mean by that, other than symmetrical ports on a Cleveland or something.
Man, you're going to have to give some dates there because
Yeah.
it was Ford, it was GM, and Ford, and then Chrysler. Chrysler kicked ass for a long. Their engines just went full bore. And then the 70s, they all sucked.
Yeah. That's Machine. Thanks. We appreciate you. That's good tech, Darin. Thank you. Mike Cranston. Now, he's from New Zealand. He says, hi, guys. Great to see you back. 3 p.m. Thursday here in New Zealand. Just put the grinder down on a set of cast iron heads for a break. DBG DMI is live. Great work.
Those boats, man. I watched that kind of racing. Those boats there, man, that's wild.
They are insane, man. Short, like 18 feet or something, aren't they? Or 16 feet.
Oh, man. Fast, reactive, and accelerate like unbelievable.
So maybe Mike's into that. He'll let us know. Let's see. Terry says, Tim, the Cathedral Port LS heads love when I do the shape Darin is talking about.
Yeah,
a wide floor and a rounded top. I think it helps a short turn also.
That's, other than a 23-degree small block Chevy, that's the highest short side loaded head there is.
Really?
Yeah. The short side is hyper critical. I mean, you want it, and that's what I was going to get into on the part 2 of the port design. You want the apex of the short turn as high as you can get it to where at least half the valve diameter, or maybe a little more, and able to give the time to make that turn. But, you know, on those heads, the short side stood up and the floor is coming up. So all the airspeed is concentrated at the apex. So its shape and width is really super critical. Any amount of area you can get there to slow that down can pay big dividends. In most castings, you can't get there.
Mark, it's good to see you here. He's from Australia. Thank you for showing up here. Now, Bruce says something. Would you shut off the vacuum pump during warm-up before a race for mist to the oil wrist pins?
No, it usually happens at the highest loaded area in the power curve, peak torque and peak power. So that's when they starve, when they're loaded. So the only time you shut the vacuum pump off and use like a braking oil is when you're breaking the engine in. After that, you should have designed into the engine proper clearances and unit loading wherever with that wrist pin piston combination, to where the little oil that it does get is sufficient. Otherwise, you're going to have to do something different. But it's only during break-in, really. Forceman
says, hey guys, question for Darin. I have a Profiler Sniper 2 9.8 big block Chevy intake manifold designed by you, sir. It's been a while since. Would there be anything you'd change in this manifold?
Yeah, that was the progression of manifolds at the time. The engine speeds were coming up.
Yep.
You know, the engine cubic inches were coming up. And the manifolds that were out there, you know, I'm having to put $2,000 in welding and sawing them up and heavily manipulating them, and it cost a lot of money. And that's where that manifold came from, was basically designing a manifold a little better than what we ended up with after a fully modified one. So in its day, it was really, really good, but nowadays we have less taper, the runners are aimed, they're straighter, there's a lot of things. That manifold works really, really good on lower RPM, 545 cubic inches, 535 cubic inches, 500 cubic inches, 7,500 and below. That's where that manifold belongs. And the Sniper is a bigger manifold with more taper. Basically, that's the only difference between the two, and it's just meant to wind up a little further. But then the Edelbrock Victor came out, it's better, but it's also designed for a lot bigger engines and even more engine speed.
Mm-hmm.
So that manifold still has its place.
So below 7,500 RPM, 500 cubic inch. What's the max? 540?
550 cubic inches. You know, a bracket guy that wants to go out and run his engine 300-400 runs before it sees the next rebuild.
Right.
It's going to keep his engine speeds down 7,500 and below.
Yeah.
And that's where that manifold fits the bill.
What year was that? What year are you talking? Do you know? Do you remember?
2000 to 2000. No. God, that would be 2010 to 15, I think.
Was it 2015? Doesn't really matter. I just
Yeah, in there
don't
somewhere.
matter. It's us getting old. So 7098. Thanks for getting back to me, Darin. I want to know if you've ever tested the passive or active pre-chamber used in F1.
Nope.
There it is.
I've studied it. It's really interesting. Takes a lot of engineering to make work properly, but yeah, I've often thought about. I've thought about what you could do with it, but I don't have the means to even test something like that.
Tom, Darin, bore diameter and piston speed aside, how much does dynamic compression ratio play into your calculating port cross-sectional area and port speed for a given combination?
It's not that I look at dynamic compression ratio more than I do the VE and the engine speed of the engine. And as far as bore diameter and piston speed aside, that's the primary, two of the primary variables that I use in actually calculating the port CSA. Dynamic compression ratio doesn't come into play a lot for me because I deal with engines, normally aspirated engines, that utilize the highest compression ratio possible for the fuel being used. So I don't have to think in the opposite direction and think, okay, this is a 9-to-1 engine.
Mm-hmm.
I don't even deal with them.
Right.
So I don't think it doesn't come into play for me.
There it is. Thanks, Tom.
I mean, dynamic compression ratio is when you have a given fuel and that fuel has limits as far as octane, its ability to be compressed without preignition. That's kind of dynamic compression ratio. That's what I would utilize dynamic compression ratio.
David says, glad to see your channel's back. Yeah, we are too. Thank you. I was puzzled how it disappeared suddenly. Yes, within probably about 35 minutes. I noticed on the NA combustion chambers that Darin does that the quench pad edges are rolled into the chambers. Why?
I would have to see the chamber that you're referring to.
Yeah.
On the intake side, they're sharp. On some of the exhaust side, it will be slightly radius. On nitrous chambers, it will be heavily radius. And with a quench relief cut, or the soft chamber, it will be radiused even more. So it depends on the radiusing that I do is proportional to what that engine is going to be used, its fuel, whether it's nitrous, supercharged, or what have you. So I'd have to know see the chamber you're actually referring to here.
Okay.
Now an NA, a totally unlimited NA won't be radiused at all anywhere. Maybe a little bit on the exhaust, maybe, but.
Now, if you remember that question we were talking about, Ed's machine, he said, hey, your dyno, what your dyno stuff, what dyno do you use or whatever? He's talking about the data acquisition. Are you happy with it?
The only one I've ever really been happy with or comfortable with would be DPAC. I think personally, in my personal opinion, that Superflow is overcomplicated and has a lot of pitfalls. especially with the filtering. I've never even seen a DTS, their early proprietary system. You know, I had somebody, you know, it's like I said, what was the statement? I said that Pro Stock engines making 1465 horsepower. And one of the guys says, well, no, it's not. And I said, what makes you think that? He said, well, so-and-so with his DTS makes 50 horsepower less. And I said, well, if you do the basic equation, force times mass acceleration, yada, 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 there's power. If you have a given mile an hour, it takes X amount of power to achieve that, regardless of what your dyno says. So his data acquisition system is 50 down. That doesn't mean they're not making 1465. It just means on his dyno, he's only making 1420.
What type of surface finish is better on ports and chambers, even piston crowd for ethanol fuels?
Man, we went back and forth for decades on the polished and rough and textured and this and that. And polishing is not good. If the engine is using a little oil, it will just adhere to the piston. It won't carbon up. I mean, a 60 grit finish is more than sufficient for anything. I've never found it anything better. Polishing is not good. I mean, I've polished stuff to a mirror finish, and did it make any more power? Did I see anything? No. Didn't see a dang thing. But what I did see is oil accumulation in the chamber. It couldn't carbon up.
What do you think about, though? Does the ethanol fuel come into play at all?
I don't know. I have so little experience with ethanol fuels.
Pontiac 411. On the small block Chevy head, do you find any gain by making the roof of the pushrod pinch wider than the floor to help equalize airspeed through that area?
Yeah, you can do that. Absolutely.
Yep. Budget Pro Mod. I have a set of GM old Pro Stock Pontiac PD. Wow, Larry. Heads with the exhaust move over 80 thousandths on supercharged 1471 big block Chevy 555 230 188 square intake port. Should I upgrade to oval port?
Man, those heads, I mean, that's like circa 1988,
9 or something, or
89?
Right?
Yeah.
I had him on for a live chat.
You know, the EPD heads that we had in Pro Stock in 90, 91, 2475, 1850s.
Yeah.
Was the size. All square, slow, you know, and we oval ported those things when we went to the Ford Core, and Ken, that was right when we went from this big block Chevy to the Ford Core. Yeah, it was a gain. An oval port is better than a square, just so long as it's not too small.
Okay.
It carries the fuel so much better. Sometimes the lower the port gets, you know, like a Hemi, the small Hemis are square ports. They're not oval. Well, a square is 22% bigger than a circle, and you have to have a given amount of area, so you're just forced to use the square shape.
Well, there you go, Pro Mod. Now, we were talking to Mike Cranston from New Zealand. He said they're called sprint boats.
Okay.
The top boats now are 13 feet long, 9-inch pump, and between 1,000 and 1,400 horsepower. Normally, don't see over 7,000 RPM. The acceleration is insane.
I had no idea they were making that much power.
I can't even imagine it. Who the hell's going to get behind that thing?
A 9-inch pump.
You know? So that means they're jet boat then, right? 9-inch
Yeah.
pump.
Yeah, the jet's efficiencies, his jet's efficiency, we see over 7,000, so his pump efficiency is probably 7,000, 6,800. When I did, there was a jet boat in Pro Stock Jet, drag boats.
Yeah.
And the boat was called Head Over Heels. And all these guys were buying Pro Stock engines. Well, the pump's efficiency was 8,000 RPM. And it's basically a torque converter.
Okay.
So just make horsepower at 8,000, and these guys were spending 35, 50 grand on Pro Stock engines.
Jesus.
That were peaking at 9 grand. 9,200. Yeah. Well, they had their torque peaks at 8. Well, this guy ran away from him for 3 years and just left him in the dust. Put the engine, just build the engine's efficiency curve where the pump needs it.
But at 13 feet long, think about that. You know what I mean?
Yeah, that's nothing. That's nothing.
Who the hell would get in that thing? Jesus. Ty's got a question on the old cast iron W2 Chrysler heads. Have you ever messed with them? I'm curious what your approach might be to porting them or what you think their shortcomings are.
I haven't really messed with a lot. I don't think I've even done a set of super stockers.
Really?
W2s. No.
Okay.
I mean, I've done 426 max wedges. I've done 440. I've done Hemi stuff, but I've never done those.
Well, we know they can make over 800 horsepower because that's what Glidden ran in 79 on his Pro Stock 335 or whatever it was, 334. So they do work. I do have pictures of them too if you're interested in them, Ty, from Larry Moe. In fact, I'll tell you something. I have his tunnel ram sitting over there on the workbench from 1979, his Pro Stock car. Larry Moe sent it to me. So if you
Larry Moe's one of those guys. He's the guy that coded PipeMax, the software that everybody should have in their toolbox. It's Max Race software if you want to know where to get it.
Mm-hmm.
But he's one of those guys I often say there's nothing more common than unrewarded genius, and he's one of those guys.
Yeah, and the nicest guy too. You know, I should I'll make a reel of that. That's the cylinder heads. I have the flow sheets that he had from back then, and that tunnel ram. I'll get making a video on that. Force fed. One more question, guys. When you have oval ports, if you can't gasket match intake, that will cause a lot of turbulence if the intake is smaller oval. If so, what would this cause?
Okay. In the mid-90s, a lot of people had the 14, 18-degree spread port dart heads.
Mm-hmm.
And that's about the time he started coming out with the Big Chief, the oval port, and all the manifolds started going oval port. Well, if you bolt an oval port manifold on a square port, that's 25 foot-pounds of torque, about 30 pounds an hour of fuel flow, and it will go a lot faster. And then if you oval port them and match them to that, that's 35 foot-pounds of torque. So you can bolt an oval port to a square, but you can't bolt a square to an oval port head. You can't have any wall present itself to the airflow. But why did that work? You're increasing the average airspeed of the system, making it more reactive, more signal.
Yep.
Closer to where it should be.
There's a dyno acquisition software called Your Dyno.
I've seen that. I've never played with it at all.
Thanks, Shelton Bars, 1022. Jeff Ott says, does a loss of 5% intake port flow when testing a straight runner sheet metal tunnel ram mean I have more work to do?
5%. Yeah, it shouldn't really kill it almost at all. 1% would be about as much as I would want to put up with. I would start asking myself why. what is that runner altering in the port to make it do that? Yeah. I think you have more work to do.
There you go, Jeff.
And it depends on, is it even with the runner, the port roof, is it aimed up? Is it, is there a lot of intersect angle there? Could be a lot of things, but the runner should flow more than the port, and it should only kill it about 1%. Well, 1% on an unlimited deal. It shouldn't kill it 5%.
So now we get the rest of the story.
And what I would do is I would start going in and figuring out what changed in that port, the airspeed over. Okay, if all the air is going to bore center and it's the velocity gradients and the port map, and you throw that on there and it skews it, well, why is it doing that? And what do I have to do with that port to correct it? Or do I correct it with the port and just build the manifold differently? Yeah, I think you got more work to do.
There it is. Now for the rest of the story. Now, Ed Machine asked this question a while back, and now we finally have the whole puzzle put together. It's a company that's new with the name of the company, Your Dyno. That's what he was trying to ask. Not that you had a dyno in your backyard or BS dyno.
Is it something like Mega Squirt, where you have to build it and code it? They would do all the stuff yourself?
We don't know, Ed. Only heard about it. You know what? We could find out about PRI. I'll put that down as a note. And then we can talk to him. Jacob says, when one doesn't have access to the dyno, what is the best approach to tuning at track as far as staying efficient in your actions?
Ooh, boy.
One change
many variables you can't control at the racetrack. Yeah. And if you don't have a consistent car, if you don't know that car like the back of your hand and you've made thousands of runs in the thing, that's difficult. The one thing you need to do is document. You have your track book. You documented all your barometric conditions for each run, track conditions for each run, and all the changes that you make. Those books, every pro stock team in the world had their track book. And when you went to that track the next year, you pulled that book out and you ran through the pages. Okay, this is what I did last year under these conditions, and this is my clutch setup, and yada, yada, yada. But it's only good for a short duration of time, a lot of times, because let's say they make a new rule, they change the clutch. Well, your clutch data is out the window, and you got to relearn it. But write it down. You can never have too much data, but you have to get a library of data that you can work with and work from. Otherwise, you're just guessing.
This is mine, 44 years of racing from back, well, not that, 27 from 98. Kept every run. Write it all down. David Reed. It's good to see you, David. Hello, guys. If I have a bent runner, does air go around it the same if the engine is pulling it than it does when a blower is pushing it?
There is no such thing as pulling or pushing. There's no such thing as a vacuum. There is only pressure differential, period. There is a difference in pressure. Whether it's coming from pressure up top or a negative pressure down below or a little bit of both, it's the same thing.
Okay. Tom, if you're doing an aluminum set, do you bias bowl so it's wider on the chamber wall side?
Chamber wall side?
He may have some more.
You mean cylinder wall side? Or bore center side? Bore center? Well, it depends on what the port layout is, but normally bore center on most of the cylinder heads that I work with or design bore center wall straight, and you make your volume gains off the push rod side. It's like designing a manifold, which we'll get into on the APS deal.
Mm-hmm.
But the roof is straight, the high-speed wall is straight. In other words, the bore center wall is straight, and all the volume gains upstream that you do is made off of the floor and the push rod. The floor and the high-speed wall must be straight, dead straight, and you manipulate those other walls to get your taper and aim. Basically, that's how we build all the manifolds. But how you bias the bowl, boy, that's a loaded question. Depends on port height, depends on the architecture of the cylinder head, but you're always going to bias it somewhat. The higher the port, the less bias you have. The lower the port, sometimes you have a huge amount of bias. Depends on the amount of bias you have is really directly proportional to the valve guide center line and where that port's at. So if you have a port that's offset to the valve guide center line a lot, you're going to have a lot of bias in the port. If it's really straight, like a Pro Stocker, you're going to have very, very little. Yeah. How long have we gone? It's got to be 2 hours.
Only 2 hours and 46 minutes.
Only?
Only. I'm just saying, let's see how many more questions. There's only probably like 5 questions, maybe. Think we can do 3 hours? Yes,
he has. Yes, I can definitely say that I'm a student, Larry Moe.
Telling you, he's
a lot of us.
He is a great guy. There's no doubt about it. Just talking to him on the phone, he's got that Louisiana drawl. You know what I mean? I just like to talk to him. Yeah, can you imagine putting that sprint boat thing in an AC Cobra? Yeah, Shelby he would love that. You know? Yes, Larry Moe is a badass. No doubt about that. And I've asked him to be on here before, but he told me he's kind of camera shy. He doesn't really know if he could do it. So I'll ask him again. Darin, do you use flow balls? And if so, how do you interpret what you're seeing?
Okay, I use flow balls and disruptors both. So if you had a short side and you stick a flow ball in there, the flow ball is designed to take up area without disrupting the airflow too much. So what it's going to do is take up area. So it's going to tell me that more so than anything else that I need to, if the airflow goes up or stabilizes, I might, more so than anything else, need to fill that area in and make it smaller and faster. But a disruptor, however, tells me what the airspeed's doing and how it's conforming, and the disruptor is like that. So that is a vortex generator. So if my short side is too abrupt, let's say you have a hold on a second. If you have a short side that's like this, the airflow is going to break. Okay, you're going to get airflow separation here, and it's just going to be dead. So if you use a disruptor and you put the disruptor like right here, that vortex generation will make it conform, and the manometer will drop, the flow will go up. So that's telling me that either I have too much roll here, or this is too abrupt or too small. I need more layback on the short turn. it can point me in directions. But the flow balls themselves are basically there to take up space to tell me if I need to shrink it up a little bit.
Okay. So Don says Gerald Brand Racing, he has a channel, had to go to your dynos to support his dyno that was obsolete, like my friend's Land and Sea. So
I've never been on a Land and Sea dyno.
I've never been on a cruise.
I'll never go on a cruise.
All right, here's one. Let's see. David says, I noticed the chambers on DragBoss's Cleveland engine with the bore scope. I'm working on Edelbrock RPM CNC chambers for a Pontiac, naturally aspirated 12.5-to-1, 467 cubic inch. Leave the quench pads flat or radius the edges?
Flat. Flat and sharp. Those sharp edges are shear points for the fuel. That will bust the fuel up. Anytime you have like a sharp edge, if you've got big droplets coming in here, that velocity shear at a real sharp edge will just fan that up and bust the droplets. So I make sure that on NA engines, like especially something like that, they're dead sharp.
And it's good that you watched that video, because when I did the bore scope, you can see the quench pads. When I go in there with that scope and turn it 180 degrees, you can see the valve, you can see all that stuff. I wondered if people paid attention to that. Thank you, David. Bill Ferretti says, the paved dyno doesn't lie or mislead. Good night, guys. Happy Thanksgiving. Long day tomorrow with family and friends. Thanks again. We're joining the group, waiting on the new card. Well, thank you. We appreciate you being here. Let's see. Is that it? Yeah. I know I saw some question up here way up, and I just don't know if it's something I can go back to. Someone had asked a question early on, and I passed it because you were talking. And if I don't see it, it's not the end of the world. Somebody kept mentioning NetStat and computing. I don't know what that is. Do you know what that is? NetStat and computing. NetStat is a command line network utility that displays network connections for transmission control protocol, routing tables, and numbers of network interface and network. I don't know if that was something to do with being hacked.
Yeah, as far as clearing the IP stack and NetStat you can go into your command on a Windows-based computer, and there are a bunch of commands you can use to see where all the IP routing is.
Okay.
And I'll actually clear my whole IP stack, like when I'm doing something, messing with cards. And
so let's say if you get a virus or something and you go to that, then you can see the IP address of where it came from is basically what you're saying.
I'll send you the command line syntax, and you can type it in.
Well, 2 hours and 53 minutes. Let me just make sure there's nobody else that we missed. And thanks for all the answers. Pontiac, make sure you become a member at Knowledge is Power. Sounds like you have a lot of questions that we can answer there. At least Darin can. So that'd be nice that you could be there. Jeff says the scope's amazing. Yes, it is. You know, Darin and I have an Amazon store. I've been building that up with products that I've used so far. He's going to add to it some electrical stuff, whatever he decides. So we put that. I'm going to put it on I put it on my page on Facebook. So if you want one of them, they're on sale right now with Black Friday being Friday. It's like $80 for that scope. It's 1080, 180 degree articulating. I mean, it's amazing scope. So think about that. So I appreciate you guys being here. Tom, thank you for being here. We're glad that you're here. Ty says, thanks you guys, you rock. Thanks, Tim, for always asking my questions, and thanks, Darin, for asking and addressing them. Both glad you're back in action. And we are. We appreciate you being here. You know, we're here for the long term. Like I had said earlier, you know, Darin's eventually going to be here full time. I think that's what our goal is eventually in the next 2 years. I'd like to do this for full time, you know, and I think we can with all the avenues that we're going to do. The next thing we're going to be on is going to be Instagram. We're going to be on Twitch, all these other places. So you can come and find us there. We're going to start a school program, which is probably going to have some virtual porting on it.
It would be nice to be able to go into a shop and my only job is showing and training people how I do this.
And that's it. Cool. It can be done. We travel around the U.S. in our motorhome and go visit people and make videos and do virtual porting. Or hey, you know what? You got to start somewhere. Dream big, be big. That's what I always say. So I appreciate you guys being here. Have a great Thanksgiving tomorrow. Be with your families. And make sure you give God thanks for what you have. Because you know what? It can be taken away in the snap of a finger.